seasonal to seasonal prediction, as well as climate change impacts, or climate scale variations, let's say. So what I did was I went back and I looked at what percentage, or the 35 recommendations that we have, how did they map onto the IWTC 10 topics? And so that's listed here in this bar chart. So I have the 6 topics along the x-axis of this bar chart, and so I've just basically counted the number of recommendations that I could map onto each of the IWTC 10 topics. And as you can see, topic 4 has the most recommendations mapped onto it from IWTC 9. But that's maybe not surprising. It has 2 large topics, TC track as well as formation. Often there's a lot of recommendations that target those ideas or those issues. Plus, it also includes the probabilistic approaches that the TC-PFP is meant to address. There's also a lot of duplication across topics 2 through 4. That includes intensity and structure as well as formation. A lot of inner core processes, convective and boundary layer structure, and so forth. There's a lot of overlap across those topics. In topic 1, of course, is very airborne and spaceborne centric, as we talked about yesterday. Targeting observations is another topic that really was focused on this topic 1. Topic 6, of course, has, as I mentioned, the sub-seasonal to seasonal and climate scale research. A lot of recommendations toward development of data sets and attribution studies. And then topic 5 has, which is the forecasting hazards and impacts, that has the fewest number, but I would argue they're in many ways the most wide-ranging. And you'll see an example of that in a minute. I'm not going to go through all 35 recommendations here. I'm not going to read through that, but I do have those in the slide deck at the end of this presentation. And so you can feel free to refer back to that. It's on the SharePoint, and I'm assuming it's also going to be on the website too. So if you want to read each of the 35 recommendations, you can see it there. But what I will do is I'm going to talk about what I did to track the progress of these recommendations from IWTC 9. So what I did was, I went back, so the topic leads very graciously went back, and they looked at the IWTC 9 recommendations and just put in some statements on where they thought the progress had been made or had not been made for each of those recommendations. And with that guidance from the reports, I was able to subjectively essentially say, okay, for this recommendation, we've made little to no progress, and I flagged that with the red color. If there was some progress made, it was a yellow, and then if substantial progress was made, or maybe it was even completed, I gave that a green. So again, this is just subjectively determined by me. Some of those will go back and maybe they'll have a different interpretation and identify a different level of progress, but at least this is what I came up with. But you can feel free to do it yourself. And there were a few cases where there was no guidance provided from the topic lead on a specific recommendation, and so I just said that's unknown. So what I'm going to do is I'm going to go through each of the 6 recommendations, and I'm just going to show, in terms of the counts, where progress had been made and where progress had not been made. But I'm not going to go through each recommendation, as I said, but just give a couple of examples showing maybe one of good progress and one of no progress, for example. So let's just start with the first topic, topic 1, remote sensing for TC analysis. In this case, there's a little color code up here again. So of the 8 recommendations that mapped onto this topic, I said that 2 had been completed, or nearly completed, the green. 4 had had some progress made, and 2 had had little to no progress made in the red. So just some examples of like one that the topic lead said little to no progress was made. The recommendation from IWTC 9 said, encourage the growing number of research and operational programs that are providing validation data for radar-derived, aircraft-derived, and satellite-derived surface wind speeds and vectors outside the Atlantic Basin. These efforts would include support for validation and development needed for assimilation into NWP. So the topic leads wrote, it's still difficult to get a wealth of observational data from some networks, perhaps mesonets or buoys. So I said, I identified that as little to no progress. But an example where there was clear progress and actually something was completed was the second recommendation here, to encourage and support another international workshop on satellite analysis of tropical cyclones, IWSAT-C, in the future, expanding the role to better reach underdeveloped TC-prone countries to provide information on the satellite sensors, data availability, data accessibility, and platforms, and to develop training for how to use the products and applications. So in this case, we actually did have an IWSAT-C 3 that was held a year ago, December 2021. So clearly this was a success. We were able to accomplish that recommendation. Let's move on to topic 2, TC intensity changes. We're going to talk about that this morning. One of the recommendations was to expand the verification beyond current WMO guidelines to identify difficult cases of TC genesis, track, intensity, structure, and impacts. Such cases, as well as the metadata explaining why they were difficult cases, should be collated and stored on a community-based database for subsequent research by, for example, involving the research group on forecast verification. So the topic leads wrote, WMO forecaster is difficult in extreme cases. So I guess the website was provided here. It requires updating and promotion as there's uncertainty of how much it's used by the research community. So that suggests some progress has been made. They've set up a website, but more work needs to be done to make sure that it's updated, tracked. Another example is the second recommendation. Continue research on secondary eyewall formation, eyewall replacement cycles, and associated structure and intensity changes to guide operational forecasters in the likelihood of SEF and ERC, what wind field changes may occur, and whether the ERC will complete. So the topic leads wrote, a substantial amount of research has been done in the past 4 years on SEF and ERC, including understanding the mechanism to trigger SEF. Main tools for forecasting ERC are PERC and MPERC, which are probabilistic ERC onset tools developed for basin. MPERC works on all basins. I'd say that that's a clear example of definite progress that's been made. If not completed, at least there's substantial progress. So that's another success story. One thing I want to point out here is, marking some things as not having, little to no progress has been made all the way up to success. I would argue that we don't want to have all greens, because that suggests that we weren't ambitious enough in our goals. At the same time, we don't have all reds. So I think the optimal combination would be some greens, but certainly a lot of yellows. So some progress, but we need to keep working forward. We want to be ambitious in what we're targeting, which is not overly ambitious to each one of those. So there's that sort of balance. And you'll see in the end here, I'll get to some of these. Okay, topic 3 is TC structure change and latitude interactions. So an example where little progress was made was to develop a definition of extratropical transition that builds on cyclone base winds. So that takes into account the different pathways to the T. So the topic leads wrote, there has been little progress on this recommendation. Furthermore, it is now suggested that a holistic approach that can identify multiple types, including subtropical transition pathways, including tropical transition, should be undertaken. This is interesting. There's a couple of these. It is suggested that this recommendation be carried through as a recommendation for 10. This might be a good opportunity for a specialist workshop bringing together researchers and forecasters to discuss, facilitated perhaps by the working group on tropical research. So that's again an example of little progress has been made, but there are suggestions on maybe how to move forward. Another example is the second one. Routinely analyze radii of maximum winds and 34 knot winds and include these as best practice parameters and post these in best practice databases for all basins. Standardized methods should be developed to guide the evaluation of these parameters and errors. Topic leads wrote, a questionnaire was sent to several operational centers. Out of 7 centers, 4 were routinely analyzed RMW. 2 do not routinely analyze RMW, and 1 analyzes RMW but does not post quality proposal. There's currently no standardized method to guide the evaluation. So again, some progress. Okay. Topic 4, TC track information incorporating the TC PFE outcomes. So one recommendation said, continue research on the interactions and processes that impact TC track. And I chopped off a little bit, but basically the topic lead said limited progress has been made on this topic. So that's interesting. The idea that there's not a lot of research happening, for example, in TC track. But another more clear success story is consider working toward replacing static cones of uncertainty with dynamic types, which can be ensemble-based or hybrid statistical techniques. Topic leads wrote, most agencies have either implemented some kind of dynamic forecast confidence cone or are exploring testing techniques. That to me suggests that definite progress has been made, maybe not completed, but certainly almost done here. Topic 5, forecasting hazards and impacts including landfall. So this was the one that had the fewest number of recommendations. One of them said additional efforts should be spent to improve region-specific forecasts and actionable information on tropical cyclones and associated landfall and new development parameters. So this is the topic leads wrote. In the USA, research is continually conducted on improving forecasts for TCs and their associated hazards. Also, at RSMC New Delhi, following steps have been initiated during the last 4 years to improve region-specific forecasts. One on described some of these examples. Some forecast systems, dynamic or statistical techniques, specific rainfall, and so forth. So that would say to me that clearly there's been some definite progress. Another recommendation, coordinate researchers, operational forecasters, and social scientists to jointly work together to design early warning systems using impact-based forecasting techniques, taking into consideration the decision-making processes, cascading TC impacts, forecast uncertainties, and varying capacity to respond. That kind of sounds like the theme of this whole workshop. So the response from the topic leads were Fiji's weather-ready nations provides an example of an initially qualitative impact-based forecast. Weather-ready nations is a multi-hazard impact-based forecasting system. The USA continues to invest in social science integration within the TC forecast process. Gina talked about that yesterday. So another definite example of significant progress on this topic. In fact, for this topic, I marked all three of those recommendations as definite success, near the completion. And then the last topic, topic 6, tropical cyclone variability on the synoptic scale. So the first recommendation, expand the evaluation of the skill of climate models and representing TC activity for monthly climate change timescales using standardized verification techniques to allow comparison of different methodologies. Involve WMO verification groups and TC subseasonal verification and encourage the sharing of verification codes. The topic leads wrote there has been a large effort in the research community to evaluate operational subseasonal forecasts of TC activity, including the skill of predicting TC genesis and probability of TC clusters. The involvement of WMO verification groups and sharing of verification codes is not yet taken place. So definite success, but not fully there yet. More research on variabilities and various timescales that are important for subseasonal TC activity forecasting is recommended. This one, the topic leads wrote, there has been a large effort in the scientific community towards understanding the sources of predictability of subseasonal timescales beyond the normal modulation of TC activity by the Madden Joint Organization. A lot of progress has been realized since IWTC-X on better understanding the role of tropical and tropical interactions to improve subseasonal forecasts. So a lot of progress has been made, I think that. So where do we stand across all 6 of these recommendations? So these are the total numbers. I just added up my reds, yellows, and greens. And I came up with, as you can see, 8 recommendations had little to no progress made. 14 had some progress made, and 13 had substantial progress. So that's pretty good, I'd say. Maybe a little bit more reds if we'd like to see. I think we'd like to see more of those reds into the yellows. But we still, suggesting that we still have some work to do. We have pretty ambitious goals, but not, perhaps maybe a little overambitious for some of those goals. The progress or the lack thereof is, I didn't really go into this, but they're fairly evenly spread across the research community, the operational community, and the WMO. So it's not like just research is not doing what they need to be doing. It's pretty evenly spread. There was little progress in research on track, which we talked about a little bit, on extratropical transition, defining SCF and ERC genesis. And some of the suggestions, which I gave an example of, lend themselves to possible workshops, for example, the SCF, ERC definitions, or transition. Workshops seem to be a good way to satisfy these recommendations. For example, IWSAT-C was a nice illustration of that. So perhaps there are some other future workshops that could be proposed, for example, that could help us really satisfy some of these. I think that's all I've got. And again, if you want to see the poll list here, I'm not going to go through it, but feel free to read that. So Kim, we have a couple minutes. Did you want to come up and just give a little commentary on what I presented, and maybe that can help to guide us for
Thank you. So for those of you who don't know me, I'm Kim Wood. I'm from Mississippi State University in the United States, and I'm serving as the recommendations chair for this workshop. I am responsible for all of the documents you've been hopefully able to click on and things like that. So yesterday was a learning experience for a lot of us, especially me. I am refining the instructions that y'all are getting to make sure that we are facilitating conversations oriented around the goals of this workshop. So as Rob said, the outcome of this workshop, a huge portion of that are the recommendations. So on Friday, you may have noticed that there's an entire session dedicated to recommendations. When we have gone through all of the suggested recommendations, the recommendations committee, those of you who are on it, thank you so much, we will present them to all participants to be ratified so that those 10 recommendations in the context of the 11th workshop. So some of the motivation for this is it should help direct some of our efforts over the next few years, because by having these conversations, especially in the breakout sessions, we finally get a chance to give input on what are challenges that you're facing in research, in operations, what types of things are useful in research, in operations. Researchers don't necessarily get the chance to talk to operational forecasters on a regular basis, so take advantage of these opportunities to have those conversations. For those of you who are in research, consider using these recommendations as motivation for proposals that you put together. You have conversations with program managers, with those who could provide funding for the efforts that we highlighted as a community that we need to pursue. Ideally, there's some breadth of scope. You may have noticed that a lot of the draft recommendations are a bit on the specific side. Consider how might we look at that as highlighted as a need, but while considering the varied resources that are available across this community. Not everyone has the number of people needed to pursue some of those goals. Not everyone has the financial resources to pursue some of those things. So keep in mind sort of the diversity of the membership of WMO as represented here at this workshop. Also, some overlap is fine. These are not recommendations from specific topics. These are recommendations from the workshop. So you may notice, especially today, I'm actually really happy that intensity and structure teams are all on the same day, that some of the recommendations from the intensity side of things look a lot like some of the recommendations on the structure side of things. Those could potentially be combined into a single recommendation instead of being separated by topic. And that could actually foster some interesting collaboration. So when thinking about these recommendations, these draft recommendations that we presented to you, we get to discuss in the breakout sessions, keep in mind what were some of the things that we did make progress on in the last 4 years? What were some of the things that we struggled with, where little to no progress was made, and how might that inform how we think about the recommendations that are crafted here at this workshop? So in your breakouts, there are 2 sets of things that you can talk about. You can specifically focus on the discussion questions that were offered by the topic leads to help guide your conversations. You can focus on the individual recommendations, which are in the Jamboard links that everyone gets, or you can do a combination thereof depending on the makeup of your stuck in the little box. You have to answer all the questions. So again, anything would, you can reach out to me with any questions you might have. If you are a note taker, you are learned from yesterday and the presentations today. So I think that's all I wanted to cover. Thank you for letting me have the floor for a bit.
Is there any quick question or two for Kim or for me before we go into the first topic of the day on recommendations? Okay, hearing none. Thanks, Kim. That's great. All right, so my glasses back on so I can see. Okay, so now we're going to move into the topic 2, which is the TC intensity changes. So I think I have that. So Eric Blake, come on up. Actually, maybe Joe, how do we get the draft, the program of the schedule? I just kind of want to talk through that. Is that easy to do or no? Don't worry about it if not. But that's okay, don't worry about it. That's okay, don't worry about it. All right, so what we're going to do is we're going to start with this topic. So we have an hour and a half. It's 9 o'clock right now, Bali time. Hour and a half to talk about TC intensity changes. So Eric, as one of the topic leads, is going to talk about some of the higher level issues and advances with the intensity change, and then we're going to hear rapporteur reports from 3 people, and then I think Eric's going to come back again and kind of give the topic lead summary. So what we have is, again, an hour and a half. I'd like to keep each of the rapporteur reports to no more than 20 minutes each. So I'm going to give, at the 17-minute mark, I'm going to give a notification. I really want to stay on time today, so I'm going to be cracking the whip. So please make sure you're done by at the latest 20 minutes, and if you finish earlier, then that's great. There'll be time for questions. Otherwise, we'll have questions at the end. And I guess that's all I've got. So, Eric, let me go ahead and get you up. For those of you online, also, I think, Munihiko, did you post the YouTube link in the chat? Okay, so I know that there was issues yesterday with some of the audio and the video resolution, but apparently using the YouTube link worked a little bit better. So if there's issues with the Zoom today, then try the YouTube link and that should work better. And please feel free to post any questions to the chat. That should work today. And we'll try to get to any online questions in addition to questions in the room. Okay, thanks.
Thanks, Rob. So my name is Eric Blake. I'm a senior hurricane specialist at the National Hurricane Center. This is my first in-person IWTC, and it's really an honor to be here. Bill Gray was my advisor in grad school, and he always talked very fondly about the IWTC. He always said he'd send me, and then I didn't stay for the PhD, so I didn't have the chance to go. But he always thought it was a really worthwhile venture. And it's truly a career highlight to be in this room with all these esteemed people. So thank you so much. I'd also like to thank my Dr. Wu, my other topic co-lead, as well as the rapporteurs. I flipped 2.2 and 2.3. So I just wanted to say a few words before the rapporteurs gave their reports. And sticking with the theme of this conference about improved TC science and services for better decision making. So I wanted to show kind of a long-term history of where we've been with intensity forecasting. It's for the old timers, and I'm kind of getting there myself now, approaching 25 years. The first truism about intensity forecasting was, we're no good at it. When I first started, when I went into grad school, people basically were like, well, in the 1990s, we've had no appreciable skill increase in the past. I'm showing the National Hurricane Center just because it's the most easy data set that I had for a very long time. All the other RSMCs are showing similar decreases, maybe with slightly different slopes, but some decreases. So in the 70s and 80s was basically the same story, time and time again. We've seen no increase in intensity. The skills are right on, the errors are right on top of one another. One of the biggest changes in the 1990s, the orange line decreased in the low level in the beginning, and people were like, oh, why are we getting better? That was only the interpolation work. Computerized interpolation was a real benefit to getting better intensity forecasts. And even in the 2000s, people thought, early 2000s, intensity forecasts were not going to do any better. It's been 40 years, we've been trying and trying. But I'm happy to report there's really been a breakthrough. We no longer can say the intensity forecasts aren't getting better. And it's really people in this room and online that are enabling this. The better modeling is spectacular. I think it's really a true success story that should be trumpeted by all of us. And you see the big, I had many debates with former bosses about whether the pink line, the decrease from the 2000 to 2010 was real. And then you can see in the past 3 years, it's actually decreased even further. So it's a monumental success story that's filtering across the worldwide basins. And you could show, I could show the year-by-year decreases as well. Look at the JTWC numbers as well. The sharper downward line is pretty impressive. So I just wanted to set the stage here that the work that many of the people in the working groups have been doing has been spectacular and is really contributing to a lot better forecasts. So with that, I think, Chris, are you online? to be online.
I don't know if people in the audience can hear me though.
Chris, we can't hear you.
So trying one more time, any chance you can hear me in the audience?
We can hear you now.
Okay, I don't know what was going on. I apologize for that technical difficulty, but good to hear that I'm online now. Okay, so did you want me to share the slides or are you going to present them? Uh-oh.
Can you hear me, Chris?
Yes.
Yeah, go ahead and share your screen, please. This is Rob.
Okay.
Thanks. I'll let you know when I can see you now.
Okay, my apologies. Hopefully you can see the slides now.
Yep.
Yeah, you can hear me.
I can hear you and I can see the slides in full screen mode, so you're good to go. So 17 minutes, I'll give you a 3-minute heads up. If you finish earlier than that, that's great, but if you could at least finish in 20 minutes.
Of course, yeah, thank you. So I'd like to start by acknowledging my team of excellent contributors who have contributed a lot of material to this report. It's a large group, as you can see here. And especially like to thank Xiaomin Chen, a co-rapporteur, soon to be a faculty member at the University of Alabama, Huntsville, and provided excellent contributions and leadership to this report as well. So here's an outline of what I'll talk about today. It doesn't cover the entire report, but these are some of the important topics that I felt were worth stressing here. So we'll talk about some boundary layer and surface flux processes and advancements in microphysics and precipitation along with TC structure. Then I'll say a few words about intensity change theory, predictability, and then conclude with some recommendations. So I have here this viral video from a sail drone that was from Hurricane Fiona earlier this year. And so as in many high impact weather events, the lower boundary condition is an integral part of the tropical cyclone phenomenon, both in terms of supplying important fluxes of energy and when the ocean is subject to tropical cyclone winds, the lower boundary becomes notoriously complex and with intense and complex waves, sea spray and foam, which are often organized into coherent structures. And so this video kind of shows some of the complexities that you see near the surface layer. And so this has obviously been a long-standing challenge for the community, particularly in representing the drag and enthalpy surface exchange coefficients that directly relate to the energy surfaces that fuel the cyclone. So they have an outsized influence on tropical cyclone intensity, and so that's been a significant focus area of this report and research in the last 4 years. And so one of the significant challenges in specifying exchange coefficients has been in the difficulty in obtaining observations in violent tropical cyclone conditions. Some observations suggest C sub k has significant uncertainty at high wind speeds. However, laboratory measurements that are shown here have shown that above 35 meters per second, there's actually a large increase in C sub k. And this is attributed to, at least in the laboratory setting, to wave breaking and an exchange processes that are enhanced due to large droplets being suspended in air. Now, the study by Richter et al. Is also worth mentioning. So the drag coefficient has likewise demonstrated a lot of challenges for our community. And part of the issue is the small sample size, as shown in this particular study that uses drop zones. So the applicability of the flux profile method for estimating drag coefficient has been called into question for high wind speeds. Other factors contributing to this include the uncertainty in the height of recorded dropsonde data, the short vertical extent of the logarithmic layer, and the assumptions of Monin-Obukhov theory breaking down near the eye wall. So all these factors can contribute to a low bias in C sub D at high wind speeds. Other factors and other studies have indicated that things like the complex C state can play a significant role in C sub D. These include things like wave motion versus wind direction and shoaling. And so that more of the details on that are covered in the report as well. So in congruence with the surface layer, the boundary layer as a whole has been a key obstacle for the TC research and prediction communities. As an example, NWP parameterization developments have typically been keyed in on non-tropical cyclone conditions. In the last 4 years, however, there have been a lot of concerted efforts to collect observations and to discern additional properties of the boundary layer turbulence from LES simulations. One of the greatest uncertainties in PBL parameterizations lies in the specification of eddy viscosity, shown here as K sub M. So thankfully, we've seen an abundance of observations in intense tropical cyclones in recent years, including multi-level towers near coast and ocean, LIDARs and aircraft, as well as these unmanned aircraft systems. So as of the current time, we still see a significant uncertainty in flight level estimates of K sub M and how it varies with wind speed. And we believe to make more advances in this area, we're going to need to take advantage of the UAS systems that have recently been deployed and developed. So this seems to be a very promising area of development in the next 4 years. Similarly, another area that's proving conducive to our representation of K sub M in the models has been in using LES frameworks to actually assess and improve PBL parameterizations in hurricane models. And one study I draw our attention to right now is a study by Zhao Chen et al. In 2021, where they used George Bryan's CM1 LES to derive eddy viscosity profiles in the boundary layer for hurricane force wind speeds. And in this setting, you can set the thermodynamic conditions, and this LES setting has been shown to produce various quantities like viscosity, momentum flux, and so forth that are comparable to observations, and that's what the diagram on the right is showing. And so this parameterization is actually proving very helpful in improving PBL schemes that are currently in use in hurricane models and also being developed for the HAFS model. Other areas of PBL development that have been very promising has been in looking at the impact of turbulent kinetic energy in the eye wall. So there's studies by Ping Zhu that have been very helpful and vital in properly diagnosing and predicting vertical turbulent transport in the eye wall region, which is key for intensification. And so they've investigated in-cloud turbulent mixing in K-profile parameterization schemes and found that it's typically very underestimated. And so they were able to improve this through including multi-phase water and static stability computations, which reduced the static stability, enhanced the vertical mixing, and led to stronger storms and more compact storms. It's actually more recent, or another study by Zhao Chen and George Bryan that looked at TKAE in 3D simulations, kind of found a similar thing, that vertical TKAE advection is very key to developing sufficiently strong tropical cyclones. So this seems to be a pretty big breakthrough in the last 4 years. And finally, to close out the role of boundary layers and intensity change, I would like to draw our attention to now coherent structures, which are a fascinating topic just observationally. And of course, TC boundary layers are very conducive to coherent structures. We often see boundary layer rolls and high wind speeds. And one of the reasons we see this is that the hurricane boundary layer is near neutral or weak stratification. And we also have very strong vertical and lateral shears, which seem to produce very unique boundary layer roll and other type of coherent structures in tropical cyclones. And so there's been a lot of interesting modeling and observational work in this area. I do highlight here work from Stephen Guyman et al. In a particularly unique kind of coherent structure that they've identified that actually causes, through wave-wave interactions, this transport of energy towards the mean flow. And that's kind of, usually we think of coherent structures taking high momentum air from above and bringing it to the surface. And we may actually see backscatter back into the mean flow. So that's a really interesting finding. So as another recommendation from this report, we do think this is an area that should continue to receive some attention by the community. So now completely switching gears, I'd like to just say a few words about microphysics. And like the boundary layers, is a very in-depth topic, obviously key to intensity because of its role in latent heating. Right on this slide, I'm just highlighting a few process-based studies that are kind of interesting, but there's far more to dig into in the report and in the last 4 years. For example, Bell and Montgomery in 2019 studied the vorticity evolution of Hurricane Carl in 2010 using aircraft data, and they've identified a diurnal cycle where convection is stretched in the lower atmosphere, followed by a cycle of mid-level vortex enhancement by mid-level stratiform heating. So this interplay seemed to be important, at least in that storm. And later work by Michael Montgomery and company has also continued to support similar dynamics, along with the importance of cumulus congestus and creating some initial tilt to the vorticity structure. So a lot of that was focused in on genesis, but of course these principles also apply in intensity change in more mature storms. The work of Rob Rogers and Trey Alvey at HRD has been really cool. That deals with down shear reformation of the vortex in these sheared cases, a topic that will be discussed more in the next talk. But they applied some of these same principles as well. And obviously microphysics is pretty important in this. So in the interest of time, I can't really speak too much about the depth of microphysics, but there have been very significant advancements in this area in terms of the relationship to storm structure and actually the specifics of microphysics themselves, such as things like storm or size sorting and so forth. All these are very important to the distribution of latent heating and intensity and structure change. So let's switch gears a little more to general structure. Again, a topic that will be discussed quite a bit in the upcoming talks. Just on this slide, I'm focusing on an interesting study by Ku Peng that was work from her PhD, and it shows basically she divides intensification into 2 stages that might be helpful for us understanding intensity change. So phase 1 is this phase where you have angle between the angular momentum surfaces and the entropy surfaces. And during intensity change or intensification specifically, these surfaces become more aligned together. Phase 2 begins when they become parallel. And at that point, we have the Samwise moist neutrality that allows the Emmanuel theory to apply. And some recent work by the Michael Bell Research Group at CSU has looked at observations of this and found some very tantalizing results that seem to support some of these theoretical ideas. So we also know there are strong connections in internal intensity changes to other topics such as external influences, and it's really impossible to fully separate these topics. But here we're focusing on internal responses to environmental stimuli. And as one example, the topic of vortex alignment is clearly intertwined with environmental factors such as shear. And Once a vortex is out of alignment, we ask ourselves in terms of internal intensity change, how does vortex adjust and what are the implications for intensity change? So obviously this has been an area of research over the last few decades, but significant progress has been made in the last 4 years. So we know observationally about 75% of the time, RI commences in storms that are 55 knots or less. So at this stage, storms may not be fully symmetric or not have achieved vertical alignment. So vertical alignment is obviously a key step in the RI process because line circulation promotes the symmetric distribution of precipitation and increases the resilience to ventilation induced by shear. So figuring out how alignment occurs has been a significant research challenge, particularly in weaker TCs, which have a weaker rotational constraint and therefore more dominated by divergent flow. And so recent studies have focused on 2 different pathways, which actually may act simultaneously. One is more of a non-divergent rotational alignment process. And the details of the shear profile matter very much for this, a very fascinating topic. And the second pathway is a divergent pathway that involves low-level inflow of deep convection, helping to align the upper and mid-level and low-level vortices. Unfortunately, in the interest of time, I have to continue on. So another fascinating topic is in rain bands and eye wall replacement cycles. This is an area the research community is still trying to better understand. Specifically, how and when do rain bands act in a favorable sense towards intensification, and when can they be more unfavorable? And so in our report, we generally have focused more on studies that have indicated a negative impact. For example, Joshua Alland found downdraft and radial ventilation transport low entropy air downstream into the convection associated with rain bands. And so these effects can be deleterious towards the inner core and create, it can be more notable in drier and larger wind shear environments. And so other studies have shown that mid-level inflow from outer rain bands can direct low entropy air towards the inner core. And a lot of this is starting to sound like the impact of outer eye walls. So like outer eye walls, outer rain bands can also impede inflow into the inner core. And so that leads us into ERCs as well. We know from the work of Anthony Didlake's research team at Penn State that rain bands play an essential role in secondary eye wall formation. And once those secondary eye walls form, we know from recent studies, there's a significant variance in the time scale of eye wall replacement. And this is a forecasting concern, obviously. So this variability seems to be tied to the variety of environmental factors that can come into play. We also focused a little bit on mesovortices in our report that has also received some attention in the modeling community. So the original theory of this may have suggested that there could be a break in intensification from eye wall breakdown from mesovortices, but recent observational and modeling work shows that, in fact, we often see mesovortices during rapid intensification. Another area of work has been by Eric Lai during his PhD work at McGill, has been studying barotropic instabilities across double eye walls, which may help facilitate inner eye wall decay. And finally, or before we get to recommendations, just a couple more slides, I would like to talk about briefly intensity change theory. This is a theory that's kind of similar to maximum potential intensity theory, except here we're trying to understand the maximum potential intensity rate, so more tied directly to the problem of non-steady state storms that may undergo RI. So the idea is here, how strong can a storm get in the absence of negative factors? And so this is a diagram from a series of Yu-Ching Wang's papers that shows the results of his theoretical model that shows this V sub m, that's the maximum, or that's the actual intensity of the storm divided by the MPI intensity. And so storms that aren't fully at their MPI obviously are more likely to undergo rapid intensification. And the higher the MPI, the more rapid the storm development will occur. So there's been some really interesting developments by his group and other groups on this topic. which are also detailed in the report. And then finally, the report talks about overall predictability, which is, of course, a key concern in intensity change. Some interesting points have been raised in recent research, particularly work by Robert Nystrom and his advisor Fuqing Zhang in 2019. Basically, they found a large uncertainty in the exchange coefficients for surface fluxes as a major factor in predicting RI. So this brings us back to the original, first things we talked about today. And so their specific focus was on Patricia in 2015 and showed that these uncertainties gave NWP models fits. The study of Nystrom and Jute from this year shows that for intense storms like Patricia, reducing the C sub K over C sub D ratio uncertainty may actually be pretty key to improving ensemble prediction of intensity. Now, Dan Tao et al. Also worked with Hurricane Patricia, and they found that the issue of vortex structure initialization is also extremely important. So this is a topic we've heard before, but yeah, clearly improving our initialization and assimilation are probably very important for getting predictability as well. So here's a list of our recommendations. First, we recommend to develop and use unmanned observational platforms for direct flux measurements in the lower tropical cyclone boundary layer to get better estimates of the exchange coefficients at high wind speeds. And we may also find success in using parameter estimation studies. Our second recommendation is that we need more data for planetary boundary layer vertical profiles of eddy viscosity at hurricane force wind speed. So this again would benefit from UAS observations, and I would suspect that LES modeling would also be an auspicious path forward. Then in terms of the PBL, it's also important, I think, to investigate mechanisms responsible for the formation of different types of coherent structures in the boundary layer. And finally, let's see here. In terms of TC modeling, we recommend targeted observational and modeling investigations to better understand TC reformation and predictability. And then given the observational evidence on the importance of TC vertical structure and intensity change, we recommend improved vortex initialization and evaluation in the area of weather prediction. And then improved parameterization of ventilation effects in time-dependent TC intensity change theory is needed. And then finally, we recommend better observations and data assimilation methods required to reduce intercore initial condition errors and to improve intensity forecast. So that's it for this. If we have time, I can take questions, or otherwise we'll address those a bit later.
Okay, thanks, Chris. Applause. So we don't have time at the moment for questions, but we definitely will later. So I'll call up Benjamin James, I think, who's going to present for the next subtopic. Call that up on the screen. Trying to find it here. Sorry, folks, a little technical issue at the moment. We'll get this resolved straight away. Can you guys share the screen, please, in the room? Okay, so next up is Benjamin James from University of Miami. He's going to talk about external influences on intensity change. So it's 17 minutes. I'll give you a 3-minute warning.
Thank you, Rob. I am Benjamin Jaimes de la Cruz from the University of Miami in the United States. I am probably the only oceanographer in this room, as far as I know. So it's an honor to be here, and I hope in the future there is more oceanographers attending these meetings, because I think it's important to also incorporate more the ocean perspective in this complex problem, which is tropical cyclones, in particular, the role of the ocean intensification. I am thankful to the Rappaports, King Lee and Joshua Wadler for the great work that did to put this report together. And of course, the other scientists in the list that did a great job in finding the relevant work that has been done in this field in the last 4 years. So I'm going to start with the ocean influence. I'm going also to present some external influence related, obviously, to the atmospheric environment and land interactions. And probably you're already familiar with the classical example of the warm ocean eddy and how it facilitates rapid intensification in many cases when the atmospheric conditions are favorable. Well, during the last 4 years, in addition to that classical, I believe it is a classical positive feedback in rapid intensification cases, there is another environmental oceanographic factor that it's becoming or making its way into the tropical cyclone community, which is the effects of salinity. In particular, the salinitic stratification in areas of reverse runoffs, which actually increase the stability of the water column, meaning that it's very difficult to mix with the cooler waters underneath. And by doing so, the tropical cyclone is going to encounter warmer SSTs during the interaction, which actually enhances the fluxes, facilitates the recovery of the boundary layer, and also facilitates rapid intensification, again, when the atmospheric conditions are favorable. Okay, so this is one of the aspects that have been noticed in the ocean environment. Another important result is that it seems to be a dependence of the intensity of the storm and the presence of salinity stratification. In particular, some major hurricanes tend to intensify furthermore when they interact with these ocean environments. And by contrast, weaker storms, as tropical storms, actually can be weakened when they encounter these strongly stratified environments in the ocean. One distinction that has been noticed during these 4 years, it's basically that in the Atlantic, in which there has been found a statistical relationship between salinity stratification and rapid intensification cases. And by contrast, in the Pacific, in the tropical Pacific, that dependence on salinity is not as strong. and the statistical relationship is still being more important with the presence of warm ocean features, and meaning that with higher values in ocean heat content in the upper ocean. Another way that has been noticed for the ocean to affect tropical cyclone intensity is due to the presence of SST gradients. This is a concept that is very well known in other processes in the ocean. We already know that the presence of currents like the Kuroshio or the Gulf Stream and related SST gradients actually enhance deep convection in the atmosphere. And we are seeing more cases related to that in the tropical cyclones. Not only for intensification, but also for weakening. And in particular, in the Western Pacific, it was noticed that in some area there is an enhancement in the SST gradients due to inhomogeneous warnings in the area, which actually is creating a larger number of weakening storms and actually larger number of rapid weakening, just because the SSTs can get cooler very fast as the storm is moving toward higher latitudes. So the SST gradient is playing a role there in actually weakening the storm, which is also another case that we should consider, because we know that it's not only about the rapid intensification, but also about the rapid weakening, what makes the difference on decision making, whether the population have to be evacuated or not. So again, this particular example points to cases in which the increased SST gradients in the ocean can actually facilitate cases of rapid weakening. And another way that we found that in which the ocean can facilitate rapid intensification is by actually increasing the moisture difference between the ocean and the atmosphere. And actually, when this moisture difference, which we call delta Q, is large enough, actually that enhances the fluxes, and you don't need necessarily to have stronger winds to actually have the storm making the mechanical work to take it from the ocean. It's just that the difference that can actually, in a short time span, enhance the fluxes and promote the recovery of the boundary layer and also facilitate rapid intensification. And we noticed that these values in delta Q can actually occur in areas with SSTs, higher SSTs, and higher values in OHC. And actually, this is a kind of passive forcing. Actually, what the storm needs is only to move over a warm ocean eddy, for instance, over an area with the surface warm SSTs and a strong stratification where SST cooling is going to be reduced for the fluxes to grow quickly. And one study also found that variability in delta Q can actually lead to interannual variability in a long track potential intensity in the case of the North Atlantic. So it's not just for particular storms, but also in a climate sense, the delta Q is an important process. And actually, we are proposing the idea that this points to the need to actually measure with the highest accuracy possible this difference in moisture between the ocean and the atmosphere, and probably think on new ways of the intensification process that not necessarily require this continuous feedback mechanism in which the wind is progressively taking more heat from the ocean, because just that difference in moisture can actually enhance the fluxes and the recovery of the boundary layer and intensification of the storm. So one thing that I found very encouraging is that for the first time, people in atmospheric science is trying to make a connection between storm structure and what's happening in the mesoscale ocean underneath. And for instance, Wadler et al. In 2005, they were able to actually make a relationship between the distribution of air sea enthalpy fluxes over these oceanic features and then very well-known asymmetries in this community related to the imposing environmental wheelchair in the environment. So this is a connection. This is one example of collaboration between atmospheric scientists and oceanographers to try to address this very complex Earth interaction phenomena. And another related study found that boundary layer dynamics should be incorporated into any explanation of tropical cyclone intensity change in response to sea surface cooling. And in this study, actually, they conducted a number of numerical studies in which actually they used warm ocean features and cool ocean features, and they proposed this very nice mechanism on how the different, either warmer SSTs or cooler SSTs in a warm ocean eddy or a cool ocean eddy can have a significant impact on the structure of the storm and in the fluxes and the recovery of the boundary layer and so on. So it's really encouraging to, again, see the atmospheric community starting to put more attention on the relevance of the ocean. And talking here with some of you mentioned the importance of the cold wave and the impact in the intensity of the storm for slow-moving storms. But however, in cases when you have a cyclonic ocean eddy, you don't need to have that cold wave. The cooling of the SSTs can be very fast, in a matter of hours, just because the thermal structure of the ocean is very close to the surface. So we have to keep track of both the warm ocean eddies and the cold ocean eddies to actually be able to better reproduce the SST cooling underneath the storm. And now I'm going to move to the effects of the ocean waves. And there was this particular study that actually found a new relationship between wave activity and tropical cyclone intensity change. And basically, the main result for this study was that for tropical cyclones undergoing rapid intensification, young waves appear in the right front quadrant while low-level moisture flux converges in that area and produces asymmetry in the storm. So this is another effect of the ocean, and we were able to see this nice movie from the sail drone that is able to measure these complex interactions between the surface waves and the winds, how that affects the drag of the area and the convergence of flux in that region. There have been some updates on the observational platforms. Yesterday Heather mentioned all of these, and I'm not going to touch them anymore. Just I want to emphasize that the role of these structures is that they actually provide probably the only way for us to have a better representation of the ocean state in the forecasting models. Without these observations, actually the models are initialized with climatology that ignores by definition the presence of ocean eddies, meaning that the SST is going to be spurious in the numerical simulations. So by having these observations, we are able to better represent ocean features in the models and improving the simulation of SSTs. So now moving to the atmospheric, to progress in the atmospheric processes. One, you already know that the vertical shear has an impact on the tilt of the vortex. And this figure basically represents how that tilting changes depending on the magnitude of the storm. And there is more variability in the tilting and weaker storms represented in the lower panel by that blue line growing from the lower corner to the upper corner. So there has been documented this variability in the tilting depending on the intensity of the storm, and there has been progress in understanding the thermodynamics on storms that are under the influence of vertical shear in the atmosphere. And another important progress in the area is that there has been found a relationship between the alignment of the vortex in a shared environment and the rapid intensification. And there is also a relationship within the time for the vortex to align and the SSTs. And in particular, the warmer the SST, the faster the vortex align, and that has been found to facilitate the rapid intensification. Another effect of the existence of vertical share of in the atmosphere is a very well-known process for all of you, which is the ventilation. And recent work has explored the pathway through which share can ventilate the tropical cyclone warm core with low entropy air. And actually, this ventilation has been divided in basically two processes, the radial ventilation and the downdraft ventilation. And this study focused on the effects of the ventilation in the lower layers and in the upper layers to make a distinction between that. And for the case of the lower layers, they found that the radial ventilation and the downdraft ventilation are similar, have similar effects on the advection of low-level theta E into the core of the storm. And another study found that actually the recovery of low entropy air in the boundary layer tends to be a function of minimum parcel altitude in the tropical cyclone. The closer the air parcel is to the air surface, the faster it's going to be replenished by the air sea fluxes, and that's going to actually help to maintain the intensity of the storm. And also it was found that downdrafts have the most negative effect near the top of the inflow layer just because they are farther away from the sea surface. So they are not under the direct influence of the air sea flux from the ocean. And another interesting development is the sensitivity of to tropical cyclone intensity, structure, and shear properties. And it was found that the intensity response of a tropical cyclone can be a function of the intensity and both the structures. And in particular, in this study, found that the storms with compact cores near the end of rapid intensification are prone to more rapid weakening from ventilation. And basically, you have here some examples of how the intensity of the storm is sorry, I am focusing on the lower panel. You see the variability of the intensity of the storm measured in hectopascals and how that changes depending on the intensity of the storm, which you see at different hours on the x-axis. And another important result that was found in this report was that the orientation of the shear direction, including its motion, relative configuration, have an impact on the rate of tropical cyclone intensity change via the modulation of surface fluxes. And this is an schematic that shows the areas of negative flux anomalies and positive flux anomalies in relation to the presence of the vertical shear. And it was also found in another study that if shear is confined to the top of the troposphere, that actually can have a positive effect by reducing the vertical shear, which actually can help the storm to intensify. And the convectively driven outflow can act to locally reduce the shear magnitude, providing more favorable a more favorable environment for tropical cyclone intensification. And 3 minutes. And also we noticed, we found some dependence of the interaction of the tropical cyclone with the atmospheric environment. And the interactions with troughs can actually either favor the intensification or prevent the intensification of the tropical cyclones. A similar scenario can be found also in the interaction with the monsoon gyres. It's case sensitive. We found cases that also favor tropical cyclone intensification and other cases that prevent tropical cyclone intensification. So again, this is case sensitive depending on the presence of moisture, the vorticity and low-level convergence, and the asymmetry of the perturbations, and the increased outer core size. And there was also a study reporting the binary interaction between different systems and how that, depending on the intensity of the interaction, can lead to the weakening of the system or the intensification of the system. And this is a schematic showing that multiple options during these weak or strong interactions. And also, other effects that were noticed to affect the intensity of the storm was the presence of Sahara air layer effects. And in this schematic also show the dependence of the presence of an increase in of the Saharan air layer effect, and also how that changes in function of the increasing in tropical cyclone intensity. Radiation effects were also found to have an impact on the intensity of the storm. And also, there were studies focusing more on the characteristics of the intensity as the storm is making landfall. Is something that we need to have a look on that, because tropical hazards to coastals and inland regions could be amplifying in terms of these studies. And given the existing trend in landfalling tropical cyclones, and also having noticed that tropical cyclones are moving slower. So we need to keep an eye on this process. And there are also influence from the type of soil. And actually, in this study, they notice a significant variability of the intensity depending on the variability of the soil that the storm is encountering as it is making landfall. It's another area that is starting to have more attention. And also, there was development of theoretical models to try to relate the presence of moisture and roughness as the storm is making landfall. And they were able to produce these empirical models that can help to actually describe the intensity of the storm as it moves over land. So to finalize, I would like to present a summary of the summary and conclusions. We noticed that salinity stratification and SST gradients play an important role in intensity change. The transition of a misaligned tropical cyclone toward alignment is important for tropical cyclone intensification. The intensity change caused by vertical wind shear responds to the tropical cyclone intensity, the vortex structure, and shear properties. The response of tropical cyclone intensity change to throw interactions could be either positive or negative, as well for the monsoons. And the presence of SAL can have a detrimental effect on weaker storms and a positive effect on hurricane stage storms. And these effects can actually be minimized by radiation, which can make the tropical cyclone more resilient to the vertical wind shear effects. And the recommendations is nothing new. Continue making simultaneous observations of the oceanic and atmospheric environment. In particular for the ocean, put more attention on the upwelling response, which is not a process that has been largely ignored in this problem. And of course, more investigation is needed and observation are needed to try to better understand this interaction of the tropical cyclone with the troughs and how that leads to intensity change, and the underlying dynamic mechanisms by which the trough morphology and intensity can alter the tropical cyclone refer to the investigation. And we need to actually continue to look more on the effects of aerosols and radiation and microphysics to improve the representation of these interactions in numerical models. And we need a comprehensive post-landfall observation system to actually better understand the intensity decay as the storm moves over land. I finish. Thank you.
Thank you, Benjamin. So we'll have to postpone questions until the end of this session. So next up is, I guess Eric is going to come up again. Let's see if I can find it this time.
Okay, so the rapporteurs for this session couldn't attend, so I'm going to give the operational perspective. I'd definitely like to thank Dr. Zhang and Wang at the Environmental Modeling Center for putting this together, as well as the great work of the large working group to try to incorporate many of the operational perspectives around the world. So I was going to talk about the last 4 years of improvements. I have a lot of slides, so I don't want to do an outline. Too much of an outline, but I'll just go right into it because there's a lot to get through. So when we look at, I showed some of this on the first slide. So looking at the year-by-year improvements, you could see that the downward trend has been significant. There has been some leveling off, especially at the shorter term, but the longer-term trends for track error in particular are down. But if you look at the other side, for intensity, it's definitely significantly down all the time periods, especially when you go further out. And you can see the exact same trend with the JTWC. I'd like to think that we're kind of in like the 1990s of track forecasting in comparison to, if you look at skill diagrams, we're in that downward trend. We're somewhat more skillful than we were before, but not nearly where we need to be. Say a generation behind track forecasting. And this trend can be seen in many of the other RSMCs. Here's from Tokyo. They've had over the past 20 years, you can see improvements in the RSMC error. It's easiest to see it, though, if you look at the improvements versus skill. And if you look at the climatology and persistence, or Schiffer, as a skill metric, you could see that the skill has really improved from basically very little improvements, say, a decade or so ago, to 20 or 30% improvements over climatology and persistence. That's very good and consistent with the results of other RSMCs. New Delhi, they over the past 4 years, they've now started to issue pre-genesis forecasts for systems 72 hours ahead of time, and specifically the example of the nasty cyclone that started with an H. I can't remember the name of Hawkeye, but they had very good performance in terms of ahead of time and then the actual forecasts and intensities. They use a wide variety of global modeling as well as other in-house modeling, and I believe some of the HMON input from the Environmental Modeling Center, TalkTech, not an H, a T. A very successful forecast case of an extremely severe cyclonic cyclone. So let's look at so why are we getting better? And I think that's really, it's nice to see that the improvements are pretty consistent across a lot of the basins. Why are we actually getting better? So over the past several years, the HWRF upgrades have been significant. So this is just a look at the 2020 upgrades. You can look at, it's generally upgraded every year or two. The HWRF is kind of for those who don't know, it's kind of the flagship NOAA hurricane intensity model. And it's been gradually improving over the past 15 to 20 years of its existence. And the items in red are thought to be the most critical factors. The high-resolution land-sea mass have really improved. It's really important when the model knows that it's moving over land. You get a better intensity forecast if it's over land or not. But there have been critical data assimilation. I do want to emphasize that now we're making more effective use of the reconnaissance as well as the Doppler wind data. For systems within, I think it's like 150 kilometers or 200 kilometers of the coast, the HWRF is now able to take into account, to assimilate the NEXRAD wind data, as well as some of the data from now the advanced GOES satellites over the past several years. We've also had better air-sea coupling that have led to these improvements, as well as physics improvements. For this particular example, this showed the 2020 in purple versus 2019, and the intensity scale was roughly improved about 10%, depending on what you're looking at in particular. So there's a big change coming for next year. You count me a little on the skeptical side because this is a big change. We've had two big skillful regional hurricane models, the HWRF and the HMON. And we're planning on upgrading to the HAVS system with two different configurations. I am not the right person to talk about the differences in each of these configurations. I'll leave that to the rapporteurs to talk about each one. But we're having, the domains are quite similar, but they're using different DA strategies, as well as ocean and wave coupling, as well as a different physics scheme. And hopefully that will give the diversity needed. I think one thing that was a little surprising to me as an operational forecaster is that, the HWRF model has been the best for many years now as far as our regional hurricane model. But the HMON model wasn't really sold as a great model, but it's provided a lot of independent forecast skill that's led to forecast improvements. And I think it's a little bit of a surprise that model, which is a data assimilation, uses a lot of the GFS parent conditions, has been so good, and in some years is our best regional hurricane model. So we move on. And that new system is called HAVS, the Hurricane Analysis and Forecast Scheme system. And so we've done some preliminary work in how this is improved. And we've done some improvements. And I guess the short story is that we're getting there. The track forecasts are a lot better than the HWRF model. The purple is the operational HWRF, and then the two different configurations that are for testing are in the blue and the red, and the track forecasts are a lot better. However, we don't really use the regional hurricane models for track. I mean, they add some skill, but they're not. We want intensity. That's what the forecasters are looking at. We want these forecasts for intensity. And if you look on the right there, so far there's been very little impact, and they've done 3 years of sample. There is some late-breaking news. I just had an email in my box that getting better configuration, that maybe we'll be able to replace it for next year. But it's kind of a big change. You'll have to stay tuned. It's an evolving situation. COAM's TC has also been an important reason why the intensity forecasts have been getting better. It's been upgraded on an annual basis for the past 4 years, and it's done a lot better in terms of rapid intensification. You can look at, so on that diagram, you want to be as close to that diagonal as possible. And prior to the upgrade, which is a couple of years ago, it was significantly underdone, and now there's a much more reasonable, much more reliable scheme, although with that kind of skill score, we have a long ways to go. But one thing I like to emphasize is that this type of independent modeling system, independent from NCEP, it adds a different flavor of skill because it's an independent model that has skill, but it's not the same. So when you're combining things in the model consensus, it's actually more critical than one would think. It adds much more skill than something that's more closely correlated. Another thing that we started looking more at, and I think that this is used globally, not just the Atlantic Basin, is the COAMS TC ensemble. We haven't seen it, getting it into within 6 to 12 hours is sometimes difficult, but it's our first operational TC ensemble that shows some skill and some reasonable, sometimes you could see, as a forecaster, you want to see consistency. You want to see, how does this ensemble run compared to the last one? Are certain tracks on one side or the other, are they showing more, stronger storm can move to the right? You'll see oftentimes that, what I like to think is, if you ever read a discussion and you see tropical cyclone and moderate wind shear, and that just makes me scared because tropical cyclones and moderate wind shear, anything can happen. Rapid intensification is nothing happen or weakening. And in understanding that, these models are really critical for it. But that's starting to be used more. Okay, switching gears to some of the downscale models. The Met Office regional model, the Southeastern Asian model, which starts from the MOGM analysis. Two cases for the past several years, Goni and Chanfu. The red are the parent model, the Met Office model, and then the Southeast Asian model is showing better intensity forecasts using the higher resolution model for both Goni and Chanfu. That showed a lot of skill in portions of the Western Pacific. The CMA, the Chinese model, it's also undergone significant improvements over the past several years, from both a horizontal resolution increase as long as with a vertical resolution increase, and it's not just forecast now in the Western Pacific. There's also forecasts available in the Bay of Bengal and Arabian Sea, and the skill in some of the reruns has been shown 15 to 20%, which is quite significant for the intensity or reduction. Okay, switching back to the global models, the European Center, right now, several years ago now, they went to the 9-kilometer operational model, and they've now done experiments to see. Their goal is actually to get it in the 5-kilometer range, and they've worked with experimental physics packages as well as different convection packages, explicit versus non-explicit, and the operational forecasts using the operational forecasts are kind of that blue line, and then the 4-kilometer improvements, and you're talking, again, in that 20% range. It'll be a while before the computer power is available to go to the 4-kilometer, but it's certainly something to look forward to over the next few years, maybe for the next IWTC. One change that I think was kind of underestimated, at least I can only speak for myself, is that changing the drag coefficient has really improved some of the wind speed pressure relationships. So the old version of the UK Met model showed that the observations in green versus what the model would show was a vast low bias at higher wind speeds, and now more recently it's shifted a lot closer on the basis of how they've changed on the basis of the observations that show the drag coefficient leveling off at those higher wind speeds, and so we're getting better and more useful information, but again, the global models aren't really showing the same skill, but they are still adding to the forecast, but they're not quite at the level of the regional hurricane models. One huge advance from NOAA's side is the GFS, the upgrade in 2019 that showed significant improvements for both for track, but definitely intensity. So the old model is in red on these, and the new model is in the green. And large improvements, statistically significant at most time frames, and a huge number of changes to all sorts of things. It's not all great. If you've ever looked at the GFS forecast, you know it likes cyclones now a little more than it used to. And so learning that to adapt to that bias has been a challenge, but its intensity forecasts are now operationally implemented in terms of our consensus aids. It adds to our intensity consensus now, so that's quite impressive. The JMA model, they have a host of models that they run in-house and globally, and the improvements over the past several years. It's nice to see. I mean, we all have kind of the same problems, TC intensity forecasting. It's hard, but you can see the same general slow decrease. No more, we're talking about flatlining, showing the statistical significant improvements. And JMA is planning on increasing the horizontal resolution, improving the physics packages, and focusing on some of the smaller scale features. And so one thing that so this is just like a quick summary of what we saw in 2022 so far. So this is a skill diagram. So you want to be at the top. The official forecast from the Hurricane Center is that for the Atlantic Basin is in black, and then the dotted lines there are the consensus aids. And the consensus aids in general were better than any one performing model. But the blue line in this particular case is the GFS. It might be a little hard to see, but the GFS model actually had quite high skill for 2022 in terms of intensity forecasting, some of the highest we've seen. We still haven't seen some of the same improvements yet in the European Center. It's kind of on the tail end, but it's still adding positive skill to the overall consensus. One other thing we have locally that's been around for more than 4 years now is we have the corrected consensus model. Every now and again, if you look at the discussions, we'll talk about the NOAA corrected consensus, or the HICA model, as we call it. And we go back and correct, look at 5 or 10 years of depending on what we're trying to forecast, whether it's GFS, whether it's regional hurricane forecast. We go back and kind of correct it for the biases we've seen in the previous hurricane season. And one opportunity that we've had, since the GFS hasn't really changed much over the last several years, is that we're able to increase the training set for the correcting consensus. Hopefully the GFS upgrade, more significant upgrade, will happen in a year or two, but there is some back-end improvements that we're seeing. Thank you. Okay, I'm gonna have to skip. So the TC intensity forecast from JT, including when the intensity, the rapid, the RIPA is higher than a certain threshold, is showing positive skill as well. I did want to talk a little bit about rapid intensification. I knew I might get a little bogged down, but one of the real reasons we're seeing that improvement is that it's not just we're getting better at rapid intensity forecasts, at 30 knots over 24 hours. It's just that any significant changes, back in the old days, if you saw the forecast go from 30 to 40 to 50 to 60 knots every 10 knots over 12 hours, that was about as much as we did in the old days, and we knew it could be a lot higher. But now we have more skill, and so we're able to, anytime that significant intensity change, the 75th, the 80th percentile, we're starting to detect that more and more. But our false alarm rates, and this is the Hurricane Center forecast is there, but the models are there as well. The false alarm rates aren't increasing. What's really a good sign is that the forecasters are getting more confident in using the guidance, as well as the false alarm rate from the guidance isn't increasing as well. That's really a key point, is that our detection scale is low, but our false alarms aren't rising as well. So we're kind of making gradual improvements. Same with the Joint Typhoon Warning Center. They find that the best skill, a lot of times the forecasters know that rapid intensification is coming, but when it actually occurs, now that's a hard problem, because we heard earlier about the vortex tilting, the misalignment of the low and mid-level vortices. When that happens, that's really anybody's guess. But if you give enough time, say 36 or 48 hours, you don't really know whether it's going to happen in 3 hours from now or 9 hours from now, but you have a pretty good idea it's going to happen over the next day or two. And they're starting to see, as well as we're starting to see, that the skill is maximized in kind of the 2-day time frame. We expect the storm to intensify. We expect it to intensify rapidly. We're not exactly sure when, though, but that's still useful for our partners. Not so useful if it's very close to land, but if out over the open ocean, we're able to be more aggressive with the intensity forecast. So the JMA, the general gist of what I got was that the confidence wasn't there quite to the same level, and I needed to kind of talk to the working group a little more about it. But it's hard to have the confidence in forecasting the rapid intensification, and they're exactly right. The improvement potential is definitely there. BLM has a very, it's not a unique problem, but it's a very challenging problem. They specifically mentioned this example. I don't know the name of this cyclone, but their forecast was for a low to move off the coast of northwestern Australia, rapidly intensify into a Category 3 hurricane, but it stayed over land and stayed a kind of a weak system. It's not unique to them, but knowing exactly where that track is, that dependence on the track is quite significant. I talked about the improvements from the HOR from the COAMS-TC, so I don't need to go into that. And so here are the recommendations that we came up with. It's kind of similar to what we had in the first session, improving the microwave observations as well as the scatterometer and the SAR measurements. We do find it's important to regularly update the statistical models, and you heard the previous talks. They say we need better vortex initialization. One thing that we haven't figured out how to do is to operationalize and make it useful the ensemble system, the single model ensemble systems for intensity. I'm not sure whether it's going to end up being better that we have single model systems for ensemble, or whether we have 4 or 5 like track. We have 4 or 5 deterministic models that form an independent ensemble that's very useful. I don't really know the answer to that. And then in terms of the analysis, it is very important to help the forecasters and the model developers identify when these situations are going to happen. It would be very helpful to know when these models are going to fail, and they do fail, and if any lead time on this would be extremely useful. Thank you.
you, Eric. So let's now get to your PowerPoint. Perfect. Can you project the slides, please?
I wanted to emphasize one thing I thought was interesting. One finding, Ben did a really great job of showing the importance of the salinity stratification. Something I never really considered, that especially in the eastern Atlantic, the presence of the low salt water that would prevent the mixing is actually pretty critical. And some of the recent results over the past 4 years that have shown the importance in situations like Irma and other ones. Something else, something we need to focus on a little more. We're starting to get better and better, and one of the questions is, how do we keep getting better? And I think understanding some of this salinity and the fine scale differences in the ocean might be how we push it forward, but I'm not exactly sure. So the recommendations, I don't need to read all these recommendations. I think most of the rapporteurs did a very good job. But we need to know more about the boundary layer, understanding what's happening at high wind speeds. We had really good measurements up to the low end Category 1 and Category 2. But to get the better estimates of the C sub D and C sub K and understanding what happens at really high values will benefit the models. One thing that the forecasters still note at the Hurricane Center and otherwise, it's still very hard to get a model of forecast higher than, say, a 115 or 120 knot system, and they get a lot stronger than that. And it's understanding why and getting models to forecast that type of thing more consistently would be helpful. And this last observation, understanding the mechanisms of the TC reformation, especially, I mean, we saw it with Dorian when these systems are under in the Atlantic Basin. The southwesterly shear, they love to form down shear. When that happens, we're starting to see some indications from the global models that can happen. But really understanding when that's going to happen will really produce some dividends for forecasters. And then going into some of the mechanisms. I don't need to talk about every single one of these things. We produced about 5 recommendations per subtopic, and we can talk about some of these in the working groups a little bit later on. Understanding the vertical structure in the NWP, the height, size, the tilting. It wasn't that long ago that if you looked at, say, the H-WRF, all the models, if you got a really strong hurricane, they all kind of look the same. Big thing, the big eye, that wasn't particularly realistic. But now with the better DA, you're starting to see something more represented. You're seeing small hurricanes actually be small hurricanes, and large hurricanes staying large hurricanes. Understanding how this happens through better initialization and properly understanding the ventilation effects. And these are the recommendations I talked about a little bit earlier. Again, yeah, so just really operational TC model intensity consensus. Ever since that, we were able to get members, 4 or 5 members, skillful, independent members to combine together is really a lot better than years ago. And here are the discussion questions. And especially, we'd like to thought that the influence of the moderate wind shear were very important. You can spend a lot of time on that last question. I'm sure everyone's got a good perspective, but thought it was important to bring it up to the group. group wisdom, and basically how to keep things going. So I'll stop there.
Thank you, Eric. So we have time for questions. I definitely want to open the floor up for questions. Online participants, we're going to get to you in a second, but first I just wanted to see if there's anyone in the room here. John, so do we have some of the, okay.
Yeah, I'd like to sort of address the third talk and the recommendations coming out of that. So my impression of the talk is we saw like 15 minutes of great news of these trends of intensity forecast decreasing all around the world and all that sort of stuff. And then at the end of the talk, we had this sort of flash by very fast the probability of detection for the rapid intensification. And it was too fast for me to see the numbers, but the PODs are very small. So it's kind of equivalent to, so in another context, you're telling forecasters about forecasting rainfall and you're showing all these fantastic figures about forecasting rainfall. But then when it gets to heavy floods and 100 millimetre in a day and everything, oh no, we can't do that. So I'm kind of a bit disappointed in that context in the recommendation. Surely the rapid intensification should be the focus, in terms of number one recommendation for improving operational forecasts. So, it's just a gut reaction to the talk. I'm looking all the way through, seeing these improvements, and I'm thinking, the disasters that we sort of like presented on these graphs yesterday, we sort of tend to be sort of major events, rapid intensifications. So it's kind of a comment more than a question. The question is why is rapid intensification not highlighted more and sort of made the major focus of the recommendations?
I appreciate that feedback, John. I can't disagree with you because rapid intensification is very important. Please provide that feedback to the working group because your feedback yesterday when you talked about making the same recommendation. I guess in many ways people know that rapid intensification is sort of important, so maybe it was just overlooked. But of course it's extremely critical. And again, the probability of detection used to be 0%, and now it's 10 to 20%. Hey, that's a lot better than zero.
Go ahead, Roger.
What about rapid decay? I didn't hear much about that. Is that a problem?
It doesn't seem like it was much of a problem. I don't want to talk for everyone, but I wasn't. It wasn't brought up in terms of the discussions as being a serious source of error.
Is it a problem?
It's a lot bigger problem when it goes the other way.
If I could quickly address that, there actually is much more skill at rapid decay. I did a study with the Chinese colleagues a few years ago, in a different context, that we had the maps of the intensity forecast error versus the intensity change, and there's actually a lot more skill for rapid decay. It's presumably mainly due to landfall or external factors, or dry air going into the system and things like that. But the models seem to pick it up.
Land is easier. If it's over land, it makes things a lot. If you take out the land impacts, it's harder, but it's not as big of a problem.
You could have the microphone closer to your mouth, everyone, when you're speaking, I think. Is there any questions online for, let's take a moment? Nope, no, okay. Any other questions in the room?
Yeah. Yes.
Okay. Yep, we'll come back. Yeah, go ahead.
Yeah. Actually, before landfall, the intensity and precipitation process, actually that is very important because when it is making landfall, the intensity and the precipitation process, that is more crucial when we consider very complicated land situation, when how long it will be sustaining that intensity and how quickly it will be weakening. So just I'm coming to the last question, that rapid weakening or say, slow weakening. So that is also very important.
Thank you.
We've been saying we need to improve the initialization of the vortex and time. But the question is, well, how do you measure the quality of the analysis of the vortex? And if you use initial position error, there's an ironic result. At the European Center, initial position error is the highest in the models, but the 12 and 24-hour position error is the lowest. And HWARF has the best initial position error, but their track error is not as good. And the second question is about how do you use one model for intensity and another model for track? It seems, but basically you're assuming that there isn't a relationship between the motion and the intensity. And scientifically, it's hard for me to understand or justify that.
Sure, Mike. I think that in terms of the first question, the vortex initialization, I am by no means an expert on how you measure this. But it's important to get the depth of the initial vortex correct, as well as the tilt of the angle, as well as the RMW. That has gotten better over the years, but it's by no means perfect, especially the data assimilation now with the HWARF able to use drops and MINOB data. The GFS uses the aircraft MINOB data, as well as the TDR and Doppler radar data. All that's really proved very critical. I didn't show any of the slides there, but our forecasts are better when the NOAA P3 flies out there. And then with your second question, it depends on the situation. If you're near an SST gradient or you're near land, it's much more important. But if the environment is not terribly dissimilar, it's not as linked as you think. It is most definitely linked, but it's the hardest situation when track and intensity are extremely linked. But it's not all the time.
I have to get back to this idea of what is a good analysis. How do you measure it? I understand that you use more odds, you're going to get a better analysis most of the time. But how do you know you've done a good analysis of the vortex? I'll leave that as an open question.
Sounds like a good topic for a breakout session. We're going to go to online, I think, but I want to solicit also questions for our rapporteurs, Chris or Benjamin, something on internal processes or external influences. But first, Munahiko, is there a question online? Okay, yeah, get the microphone, please. Yep. Oh, did he raise his hand to speak? Okay, well, if he can unmute himself, I guess, right?
Jack, can you hear us? You can turn on your microphone on and speak.
Hello, it's my turn to say something.
Doesn't sound like Jack, but okay, if you want to ask a question.
We're having trouble hearing the audio from the room, so when you're calling us out to answer, we can't really hear you. The only one who's coming up clear is Eric.
Okay, how about now?
That's a lot better.
Okay, did you have a question, better. Jack? Or?
I had a comment, and partly for what Eric said, partly for what John McBride was saying. We are making forecasts now that when I first started as a hurricane specialist, we'd never dare make, like bringing Ida up to major hurricane intensity on the first advisory when it was a tropical depression, forecasting rapid intensification of Laura, and then real kettle of worms forecasts occasionally, where we know the storm is going to peak before it makes landfall and start weakening, but I have high confidence it's going to do that, but that's very problematic from the response standpoint if we're wrong. Now, that's one of the byproducts of the progress. John sounded like he was a little disappointed in the progress, although I couldn't hear him cutting in and out the way it was. But just from my own experience, we're doing stuff now that when I first started in 1999, we wouldn't dare do. So I'd say we've made significant progress on the intensity side of things.
Okay, thank you. Is there another question online? Okay. Do they need to unmute and speak? Okay, pick one. I don't. Jai. Okay. Oh, Jai. Yes. Jai Pang.
Okay. Yeah, so I just post in the chat. So, okay. For the past how many years? 50 years or 100, we just use one number to predict the intensity. Like it's a max 10 meter max wind speed. But while if the storm is in its mature stage, of course, maybe we can use one number to indicate the storm how strong. But while the storm in the developed stage, or some like we just talked about shear effect, so still lots of asymmetric components there. So this one number, even we estimate from the developed techniques, is from the operational observation. So for the structure part, one miss a lot for the forecast.
Was there a question there, or sorry?
The question is how for Hurricane Center, how we can move forward, can help we really understand what's the intensity of the storm. So not only just the wind speed, so the structure itself is very important.
Agreed, and I'll be interested to see what I think it's the next group if they talk about the wind radii and the size of the storm. We focused mostly on the maximum wind speed.
Yeah, and I think most people would agree that in terms of the hazards, right, it's a lot of elements of the structure, the size of the wind field and so forth that are crucial. So any other questions in the room? Andrew. Microphone coming.
Thank you. I noted the talk on HWARF and the improvement in intensity forecasts, that there were three main factors we talked about. One was simulating coastal radar. One was observations, extra observations from the GOES satellites. And I wondered, could you also simulate extra observations from Himawari to improve the forecasts from HWARF in other basins? That's question number one. I did have a second question, but it's completely different.
I'll answer that. I hope the answer is yes, but I don't know the answer to it. That's unfortunately our EMC experts aren't on the call today.
That would effectively be a request. The second question I had, if I may, was for Benjamin, and it was a simple question. From a forecaster's point of view, we talk about salinity stratification. You talk about salinity stratification. Does that end up being correlated with temperature stratification?
The question is whether there is a relationship between the salinity stratification and the temperature stratification in these cases. And actually there is a difference, typically, probably in some, I think it's gonna be base sensitive because the oceanographic conditions change from one basin to the other. But typically, actually, what makes that layer is that they occur at different depth levels. Basically, you can have a homogeneous temperature structure and variability in salinity structure that actually is creating that additional layer which prevents mixing. So it's going to be case sensitive. But actually, the key condition is that you don't need only to have a strong stratification. You still need to have warm water, right? Because it's actually what is going to maintain the fluxes. So actually, the condition is to reduce the cooling, and you reduce it by increasing the stability in the case of the salinity, right? Or by having a deep warm layer in the case of an ocean eddy, right? Or in the coastal area where there is actually warm water through the interwater column that actually prevents excessive cooling. That's just going back to your cases again. They don't necessarily occur at the same depth level.
Okay, I think Derek Herndon has a question online. Is it to speak or is it to speak? Okay. So if you unmute yourself.
I can speak if you can hear me.
Yep.
Great. Yeah, so this gets back, it kind of folds back to the previous talk, but it also gets at what Eric was just talking about, and that is that we definitely see an improvement in the model performance when we're able to assimilate aircraft data. But we only have that in maybe 20% of the storms on the planet. So we have a very small subset of those storms that we can do that with. So, how do we get to that level? But we tend to only really seem to be able to do that when we have that really high quality inner core observation data.
Eric's mulling it over.
I mean, Derek, I don't know the answer to that. I just, I guess it's a, you have to think about a reward ratio. I mean, it's expensive, and it's irreplaceable data. And so how do you figure it out with remote sensing to get the kind of fine scale inner core data that we need? I don't have the answer to that. That's for sure.
Yeah, and one of the other things we were having a discussion on the panel group here was also that the question is, if you have a perfect vortex initialization, do you always get a good forecast? I mean, is it that simple? And the other part of that was, that we still have some work to do on some of the model physics there. Getting back at the aircraft data, then this is one of the big recommendations. It comes up in every IWTC. It's come up in the IWSAT-C. Is we need to try and find a way to get ground truth and inner core observations outside of the Atlantic. And I know we always make that recommendation in this group, but we've got to figure out a way to push that forward, possibly through some sort of cost sharing, where several countries can come together in a program and share the costs of that.
Eric is nodding. So, and I agree. I would argue, too, that this is a great discussion and a nice example of the overlap. I know that there was discussion in my breakout session yesterday from topic 1 about ground truthing and in situ type of measurements in a cost-effective way, so not every country can afford hurricane-penetrating aircraft, so maybe there's other tools that we can use. So something to think about in terms of possible recommendations to formulate. So we only have a couple more minutes for questions. Is there any more questions in the room? Oh, okay, let me just see. Okay, so online, is there another question, Joe? Oh, Pete Black. Did he have his hand raised to speak? Yes. Okay, so Pete.
Yes, yes, Rob. I just wanted to mention that observing platform that we experimented with in the Atlantic this year may become available internationally soon, and that's these windborne balloons for making a virtual any place in the world. So we had some very good successes this past season with launches from Cape Verde, Puerto Rico, and Gainesville, Florida. And also before that, during the Atmospheric Rivers program in the Central and Eastern Pacific. So I'm kind of optimistic that we may be able to get in situ observations in tropical cyclones in other parts of the world with this type of platform.
Thanks, Pete. Yeah, we actually talked about that too in our breakout session, so thanks for backing me up on that, or repeating what I was thinking too.
So I just wanted, I thought a little more about what John said about rapid intensification. And there's a real debate, I think, on whether rapid intensification is just intensification. And so are you just doing a better job of forecasting a tropical cyclone? Is it really an independent thing, or is it just we're just doing a better job at forecasting in general? And so I think that's really, is there some unique processes that we don't understand in rapid intensification? Or is it something different? Well, again, it's a good debate.
It seems like Roger and I disagree. I actually think it is a unique thing because when the rapid intensification occurs, there's a very strong, it's sort of an acceleration of the system. There's a very strong, say, intensity over time. There's a very strong D intensity squared by intensity. It's not sort of a parameter, it sort of shoots right up. So personally, I think it's a different process.
Rubbish if you couldn't hear online, says Roger.
It's a rapidly accelerating system as distinct from a slowly accelerating system.
We'll talk over a beer.
Okay, time for one last question. Yep. In the room here.
Get the microphone to you.
Actually, it is not a question. I think it's more about a comment. So we are talking about this data simulation around the TC structure, and also we're talking about the couple models. Maybe it's the time to discuss the couple data simulation and also the related programs. I think that's a couple of years that the European Center and other centers, they're moving the couple data simulation, but there's still significant issue, which is the consistent analysis in the atmosphere and in the ocean. Now we're also talking about the waves. So the 3D actually have their separate estimation scheme. When you put all these assimilate fields into the couple model, it's going to be a very inconsistent situation. It may generate initialization shocks. This will cause a big bias uncertainty in the forecast. I think maybe there's a room or 1 year we can discuss these couples destination issue, particularly in the TC conditions.
Okay, that's a good point. It's something worth discussing certainly, perhaps in the breakout sessions. So with that in mind, we'll go ahead and close this topic. So let's thank our topic lead and our rapporteurs. Let's take some time and kind of stretch our legs, maybe a bathroom break and have some coffee and conversation. And let's go ahead and do that for 1 hour and 15 minutes. So 12:30 then would be lunch for 1 hour and 15 minutes, and then come back for topic 3 at 1:45. Is my math right? Okay. Anyway, so here are the questions to consider for the breakout session. We also have the room assignments and the breakout leads and note-taking leads posted, I think, outside. So please check those during the break. Here's the QR code for the note-takers and the breakout leads to get these questions. I also wanted just to take a moment. I don't know if all of you have noticed undoubtedly that each of these rooms has a name. Hopefully it's kind of obvious what these names are, but does anyone have an idea what these names represent? Okay, it's pretty obvious, right? These are all high-impact TCs since the last IWTC, all over the world. So anyway, we just thought that might be a unique thing to do for this IWTC. Anything else?
And we just restructured rooms 1, 2, and 3. So number 1 here, and then 2 and 3 are here. So Ida, Dorian, Hernan, Dorian, and Ian.
Is there a room in this room now? Is that right?
Just here.
Oh, gotcha.
So,
Okay. And there's only 2, this is what
yes.
you're saying.
So we appreciate yesterday was some noise in the 3 areas, so we've just made that 2, and here is the number 1.
Okay, so half-hour break. Please make sure you get to the breakout sessions by 11:15. It's important. These breakout sessions, as you've seen, in terms of the recommendations, formulations, are very important that everyone attend for this discussion and dialogue, which is a crucial part of IWTC. So thanks, enjoy your break, and we'll see you in the breakout sessions. Yeah, lunch, and then back here by 1:45 for topic 3.
Okay, ladies and gentlemen, we kindly ask your attention for some announcement. First, tomorrow is our excursion day. We will visit BMKG office, BMKG Bali office, and then we visit Uluwatu Temple. There is Kecak dance performance with the beautiful sunset as the background. This is one tourism spot you must be visit when you are in Bali. So for all the participants who haven't registered, please do the registration in the registration desk. And the second one, the distribution, already informed by Pak Joe. And then lunch break will provide at the restaurant. But for dinner tonight, we don't provide it. So you can have your own arrangement. You are free. Okay? And that's it. Enjoy your break.
Cek, satu, cek. Satu, satu. Cek, cek. Satu, dua. Cek. Satu, dua. Cek. Cek, cek. Satu, dua, satu. C. Cek. Cek. Satu, dua, satu. Cek. Cek, cek. 3, 2, 1, 1. Cek, cek. C. C. Satu, dua, satu. Cek. Cek, cek. Satu, satu, dua. Coba. Cek, cek. Satu, dua. Cek, cek, cek. Itu aux berapa ya? Tuh. Oke, oke, oke. Cek, satu, C. C. Ya. Cek, satu, satu, dua. C, 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 C. Udah? Udah ya? Aux. Aux 2, cek. Satu, satu, satu. Cek, satu, satu. Udah? Udah? Cek. C, 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 C. Udah pas ya?
Udah ngomong ya udah situ. Cek cek gitu.
Satu, dua, cek, cek. C, C, C. Udah ya? Ya, yuk. Makasih. Turun aja.
Ladies and gentlemen, there is some announcement that we like to inform you. For the first, we would like to remind you, if you still not yet fill the form to excursion, you can go right now to the registration desk to fill the form to join us excursion tomorrow after lunch. After lunch, we will visiting BMKG office in Bali and also seeing a performance in Uluwatu. The place is very beautiful. We will see the sunset in Uluwatu. So if you want to join us and still not yet to fill the form, you can go to the registration desk to fill the form. And don't forget to mention if you have any allergy. The second one, the local committee only provides lunch. For dinner, start from today until later, Friday, we did not provide any dinner anymore, only lunch. The third, local committee also didn't provide any transportation from hotel to Patra, from your hotel to Patra hotel. Only pick up from airport to your hotel. If you wanna go to your hotel, actually, there is a walking distance from beach, along the beach, and you go to the right and you follow. It's very close. You can walk. You can walk. And the fifth, there is Mr. Enrico here. No, yeah. No, Mr. Enrico. Okay. Ladies and gentlemen, one more time, I would like to remind you, first, if you want to join with us excursion tomorrow, please fill the form in the registration desk. And we also hope that if you not join us, you can make confirmation to registration desk. I will not join the excursion. So we know how many people will join with us and how many people will not join with us. So please, in 10 minutes, perhaps you can go to the registration desk, inform the local committee if you want to join or not for tomorrow excursion. Registration will be closed in 10 minutes. So we hope if you still want to join for excursion tomorrow, we hope you can go to registration desk. And we also would like to say that local committee only provide lunch for dinner. For dinner, start from today, local committee did not provide anymore. And then for transportation, local committee only provide transportation to pick up you from airport to your hotel, like yesterday. But from today, we will not provide any transportation from hotel to Patra. If you stay in Holiday Inn, it's a very close walking distance. Just go to the beach behind the hotel, Patra Hotel, and turn to the right. Around 5-6 minutes, you already arrive in Holiday Inn. It's very close. It's very close. And then I like to invite Mr. Enrico Sosiomaro, if I'm correct. There is Mr. Enrico Sosiomaro here? No?
Good afternoon, everyone. Welcome to the second day afternoon, topic 3 on TC structure. It's my pleasure to acknowledge the topic leads. We have Liz Ritchie here and Matt Kukas, who's online, who can't join us physically, and I'm going to pass to Liz to introduce her presenters for the afternoon.
Thank you, Joe. It's a great pleasure to be here. This is one of my all-time favourite meetings. And I'd like to start off just by acknowledging Matt Kukas from JTWC, who can't be here, my topic co-chair. Matt did most of the heavy lifting in the management and organisation of getting these particular topic reviews together. I'd also like to say a great big thanks to the rapporteurs of all of the subtopics. Their names are up there. I'm not going to say them all right now, but also the working group members that worked so very hard with the rapporteurs to put some really good reports together. I'm going to run this particular session by having the subtopic leads come up and give their presentations first without actually presenting any recommendations or breakout room questions. And then I'll just summarize at the end, basically just about by talking about IWTC 9 recommendations and what has been done to address those, and then bringing up a consolidated group of recommendations for IWTC 10. So to start off with, I'd like to introduce for subtopic 3.1, please, Ida-san. Just see if we can find this here. That's it. It's the one.
Okay, so hello everyone. My name is Kosuke Ito, working at University of Syracuse, Japan. I'd like to talk about inner core structure on behalf of other rapporteurs, Chunchie Wu and Professor Yoshiaki Miyamoto, and working group members. I noticed several topics overlapped with the TC intensity topics, but in that case, I just briefly talk about such kind of topics. Okay, so this is the outline. TC inner core development and changes. First, we talk about the inner core development and changes, except for secondary I/O formation and the I/O replacement cycles, and then secondary I/O formation and I/O replacement cycles. After that, we talk about the operation, challenges in tropical cyclone inner core structure. And finally, we briefly talk about TC inner core structural change in future climate. And the summary, and the recommendation will be given in Liz Ritchie at the end of this topic talk summary. Okay, so first, let me start the TC inner core development and changes except for the secondary I/O formation and I/O replacement cycles. Okay, so as shown in this morning, rapid intensification is an important topic in terms of intensity forecast and structure forecast. And it has been shown in a moderate vertical wind shear case, the inner core structure is tilted vertically. And then this kind of structure can be vertically aligned when the rapid intensification occurred. The detailed process is still controversial, but after the RI onset, the structure is completely vertically aligned. So this is kind of a signature of RI onset. And absolute angular momentum and entropy surface development were shown Penn et al. 2019 and Desrosiers 2012-22. And it might be related to the rapid intensification topic in a previous slide. In phase one, sporadic deep convection near the radius of maximum wind plays an important role. A very upright convection can redistribute the large absolute angular momentum and entropy. This structure or this feature is different from the later development stage in which the absolute angular momentum and entropy surfaces evolve near the radius maximum wind, and they become much more steadier. And this type of finding, especially phase one phase one feature, is confirmed by an observational study on Hurricane Michael. The other interesting finding is subgradient and supergradient wind near landfalling tropical cyclones by Hillick and Nolan, 2021 and 2022. And of course, the tropical cyclone experiences the increased friction over land, and the wind speed is decelerated over the land, but it generates a deep subgradient inflow layer. It causes the strong inward inflow angle toward the ocean side, and then it generates the supergradient wind as shown in the red area in this figure. Very interesting finding is coming from the very idealized simulation for a dry tropical cyclone. A dry tropical cyclone is a hypothetical tropical cyclone maintained by high sensible heat fluxes without moistures. So this is very idealized, which I believe should not be existed in the tropical areas. But this kind of experiment clarified the role of moisture and falling hydrometeors. Okay, so the typical feature of a dry TC has a larger width of the eyeball and radius of maximum wind and deeper inflow layer. But it seems to be the dry type tropical cyclone. But later on, Wan and Lin 2020 showed that the difference in the inner core region comes from the falling hydrometeors. That changes the entropy distribution rather than the moisture itself. So it indicates the importance of falling hydrometeors on the inner core structure, such as the radius of maximum wind, width of the eyeball, and deeper depth of the inner eyeball. This topic might be related to the outer core circulation, but several authors recently confirmed that initially large tropical cyclones tend to become a large radius of maximum, tends to have a large radius of maximum wind. Also, the environmental humidity affects the size of both the inner core and outer core circulation. There are many works summarized in our report, such as axisymmetrization related to the sea surface temperature, secondary maximum of tangential wind in the mid-troposphere, finger-like features, sporadic deep convective clouds in I region. Many others summarized in our report. So if you are interested in, please check them out. Okay, so now I'll move on to the secondary eyewall formation and eyewall replacement cycles. First, I'd like to talk about a new kind of instability found by Professor Miyamoto, 2018. He said that the curving fast flow in a free atmosphere coupled with the Ekman pumping, this kind of feature can be a possible mechanism to explain the secondary eyewall formation. In his proposed theory, the vertical wind perturbation can develop when the basic flow is flowing very fast and curving. This condition is usually not satisfied, but this condition can be satisfied in 2 to 7 times of the radius of maximum wind, where the secondary IO typically forms. And he also showed that a theoretical estimate of a positive growth rate well corresponds to the secondary IO formation in the realistic 3-dimensional model. Several other works investigated the relationship between the stationary banding complex and a secondary IO formation. Okay, so secondary stationary banding complex, SBC, is shown in the upper left side of this presentation. And like wave number 1 feature connected to the inner core area. And 79% of 84 SEF events were preceded by this SBC type of event in a 6-hour time window prior to the secondary IO formation. So these 3 figures indicate the circularity and azimuthal coverage, and it shows that if the case has a SBC has a circular and azimuthal coverage feature, they tended to become more concentric IOs. However, SBCs with substantial azimuthal coverage and circularity are not necessarily followed by the SAF. So this feature alone cannot explain the genesis of secondary IO. Okay, so this is also related to the SBC and mesoscale descending inflow MDI and SEF mentioned by many papers recently. It says the under moderate vertical wind shear condition, as you know, in the down shear left quadrant, like quasi SBC developed, according to the enhancement of convective clouds, and it forces the convective updraft in up shear left area, and in the up shear left area, MDI is connected with a boundary layer, and a new tangential wind maximum developed. So as you can see in this figure, it helps to generate a secondary IO. Some papers argue the inner IO decay. So some papers show that the wave number 2 instability might be important for the inner core IO decay. And for example, radar observations show the elliptical shapes. That means the wave number 2 barotropic instability prior to the decay of inner IO. And this central panel indicates the absolute angular momentum tendency budget, and eddy-induced transport of absolute angular momentum seems to play an important role on the inner core decay. Okay, so there are a lot of good works has been done, and intensive works has been done in the last 4 years about the secondary IO formation and IO replacement cycles. Here we list some of which, and increasing vertical wind shear brings earlier secondary IO formation, or impact of sea surface temperature, and some interesting features or a very cold situation still can give the IO replacement cycles, and other topics are included in our report. Okay, so now I'd like to move on to the operational side, analysis, forecasting, and predictability of inner core structure changes. Okay, so here I'd like to explain one questionnaire we submitted to, as we send many operational centers, as for the how radius of maximum wind is analyzed, or you are conducting analysis of radius of maximum wind. This is sent to many operational centers. And I'm very happy, we are very happy to receive many response from many centers. And first question is, does your operational center analyze RMW routinely and include it in your post-analysis best track? And out of 7 centers, 4 centers answered yes. 1 center said yes, but no post-analysis and or quality control. And 2 operational centers say no. So, and question 2 is for the group which answered that yes to the question 1. And we asked they to describe the method of the RMW analysis. And we can see some differences in a group, and there is no standard way to estimate the radius of maximum wind, but basically they rely on the microwave-based satellite image, and if the radar data set is available, they can use that. So that was the answer. Some operational centers try to use microwave-based ERC information and rapid intensification for their TC intensity forecast. And because in many cases the numerical models have been improved and may indicate ERC and RI event, but still timing is usually incorrect. So of course we need to continue the improvement of numerical models, but observations or statistical models have been used for the prediction. And MPARC, this is the CIMSS microwave-based probability of IO replacement cycle developed at the University of Wisconsin. Forecasters, operational centers, now they use this kind of tools. The Breyer skill score ranges 27 to 41% in the Atlantic and Pacific basins. And MPARC performance is, but still we need to note that the MPARC performance might be degraded in a seared and dry environment. RIPA is a statistical guidance for the likelihood of rapid intensification events, incorporating IR brightness, temperature, core size, and core asymmetry. This kind of information has been used by JTWC since late 2017. Well, we now believe that more and more operational centers try to use the high resolution information or microwave-based good information on their ERC prediction and RI prediction. Here are several examples. For example, JTWC reported a successful prediction of ERC event for TC Harrow to 2020, and BOM made a subjective judgment of the inner core decay of TC Trevor 2019 because of the evident secondary IO formation based on SSMI imagery. The result was different from a Dobrak technique analysis, but they used the subjective judgment. And forecaster can also consider the potential applicability of lightning data, but further study is needed to find a reliable lightning indicator. Okay, finally, let me briefly talk about the TC inner core structure in future climate change, future climate. The basic thing is we still do not have a consensus in terms of a TC size in the future climate. Some papers says the size should be increased, but some do not. And we believe still the situation is controversial. Of course, this is largely due to the limitation due to the resolution and the high experimental duration. And regional climate models can help the can help evaluate the impact of future climate impact. And a TC, for example, our TC can sustain more asymmetric structure in a mid-latitude for the case study of TC Faxai because of the northward moving of mid-latitude westerlies. And the other paper says a contraction and enhancement of rainfall in the inner core regions in idealized simulations. Okay, so let me summarize my talk. the inner core structure is influenced by processes involving convection, vortex structure, and environmental conditions, which are also important for the intensity and size of a TC. The processes have been investigated by analyzing observational data, conducting numerical simulation, and developing theoretical models. In particular, in recent years, secondary IO formation and IO replacement cycle has been intensively investigated. Many operational centers have utilized satellite supportive tools and available information to their analysis and forecast for the radius of maximum wind and IO replacement cycle and rapid intensification events done before. Some recent studies argue that the inner core structure is modulated by climate change, but we believe still further studies are needed. Okay, so that's all. Thank you.
Thank you, Ida-san. We'll hold questions until the end. So I won't get up on the stage, we have for our second subtopic report, Chris Noble from New Zealand.
Right, thanks very much, Liz. So this part of the session now is going to move into the outer structure of the TCs. And just before we get into it, I just want to acknowledge the fine work of the working group that you see on screen here, but also to Ben Schenkel, who I don't think could be online with us today. He's not here in person. Ben did a lot of the heavy lifting in this part of the report. So I'd just like to say a very big thank you to Ben for his collaboration and guidance. I'll get rid of it. Thanks, Joe. So let's crack into it. Just start off with an outline of the talk today. So we're going to start off by looking at what is outer structure. We'll quickly summarise the recommendations. I know that Rob did some of this morning. We also went through those recommendations from the previous IWTC to see what related to this particular subtopic. And then I'm going to just very briefly touch on the next 3 points there, effectively the structure of the report itself. We started off in section 1 of our subtopic looking at research insights. The second section looked at the operational context for analysis and forecasting of the outer size. And then the third part of our subtopic looked at future changes to outer size and structure. And we won't talk about the recommendations. So first up, what is outer size? Previous studies have defined it as the radius from the TC centre where you have weak winds and sparse convection, but it's not particularly well defined, and there may be a different viewpoint between the operational environment and the research environment. In general, in operations, we tend to think of the outer size as being the quadrant radii of the gales, R34. But some centres also use radius of the outermost closed isobar. Whether that's supplied publicly or not is a bit variable, but that is used internally in some of the TC analysis techniques. On the research side, there appears to be no single metric that's used, and that's largely due to a big variation in the available data through the historic data sets for cyclones. In terms of the recommendations from IWTC-9, these were the ones that we pulled out that were most relevant to this particular subtopic of the report. Again, I think Rob put some traffic lights on these this morning. I would say that all of these, to a certain extent, are still relevant. I don't know that I'd tick any off at this point. Work has obviously been done on some of these recommendations, but I think in terms of all of them, could still have future work against all of them. So we kept those in mind as we were working through writing the report, and some of them will come through in the recommendations for this particular conference as well. So launching into the first part of our subtopic report, it's looking at research insights that have come through in the last few years. One thing that Ben was quite keen to stress was that you know, we've got a lot more data sets now. There are new data sets, particularly for reanalysis data sets, that are proving very useful for the research community. And the figure here is an example showing a large interbasin variability in the size of cyclones. So this is based on scatterometer data in particular. The numbers down the bottom of the graph here, so at the top, the number is the number of events, and then the number of cyclones is in brackets. And so you're looking at the mean and 95% confidence interval plotted there of the size of cyclones across the various basins, and then there's also a northern hemisphere and southern hemisphere values on the right-hand side there, and then are all combined. So personally, I found this interesting to see the variability that existed between the basins. And you know, these tend to start showing up as early as Genesis in the TC life cycle. Even closer, Joe, even closer. Oh, now we got it. And then as we continue to look through the life cycle of the cyclone, the outer size often increases as the last point here, although the rate of growth does vary a lot between the basins as the research has shown. I won't spend too much time on this figure because you've seen it already from the previous talk, but as previously noted, there is a fair bit of overlap between the two subtopics, whether it's inner or outer. There's a little bit of debate about where inner starts and where outer starts. Inner finishes, sorry, and outer starts. But effectively, the outer wind field expansion rate does appear to depend somewhat on the initial size of the system. But there are a large number of factors at play, and in viewing the previous research on it, there didn't appear to be a consensus on exactly which factors were the most important. And so this was something that we couldn't really list on the screen here as saying, well, this one's number one, number two. There are a large number of factors, and it depends a little bit on the individual research that you look at or review. And as we've heard previously with this particular figure, there is a large change in the outer structure with landfalling TCs, and I probably don't need to explain it anymore as we've seen that one already. The second part of our report moved into operations and looking at some of the developments that have occurred at the operational centres over the last few years. One thing that I'm sure will be no surprise to people in the room is that there is a large range of presentation of outer structure, or particularly the quadrant radii, between the operational centres. There's no standard format when you look at warnings. So generally all centres are providing the radius of gales, but the format that they're presented in does vary. Not surprising. All provide it at analysis time, but when you review the forecast positions along the entire length of the forecast track, there is a big variation between centres as to whether the outer size via the radius of gales is provided or not. And not all centres are providing that information through the best track data into the IB-Trax database, for example. And just on the right there's a couple of examples. So the lower right there is perhaps a little more familiar with the various rings depicting the gales, storms and hurricanes through various quadrant. By contrast, there's an example on the upper right there from RSMC Tokyo, which provide both 30 and 50 knot winds. So a little bit of a difference there in the winds provided. Some other centres also provide radii for the 28 knot winds as well. In terms of the radius of the outer closed isobar, that's less commonly provided, as I mentioned earlier. and it's a lot more subjective. It does depend a lot more on the tools that are used and, of course, by the individual analyst who's analysing the cyclone, producing the surface analysis, and it depends a lot on the surface observations that you have around the periphery of the cyclone itself to help guide the analysis of that outer closed isobar. In the session yesterday, we heard a lot about the new remote sensing platforms and products that have come along, and that's one thing that we notice. There still remains a heavy reliance on satellite-based observations of the ocean surface winds to define outer structure. Perhaps not surprising, given the lack of observations over the ocean areas. And of course, NWP remains a critical component for the forecasting of the outer size and the provision of those gale radii. Again, shouldn't be a surprise. There are far too many new developments through the operational centres to list all of them here, so we've just highlighted a little summary. And again, we're reusing a graphic that we've seen already yesterday. I think Gina showed this one in one of the sessions yesterday. A lot of new products being used from satellites. I think in the last 4 years we've had new products come along. I won't go into all of those. Again, the remote sensing discussion yesterday talked about that. We've also heard about some of the improvements coming through NWP, and particularly from the ECMWF model. There's now guidance coming through for outer size for the radius of gales. JTWC have a new climatology and persistence model that is guiding the wind radii along the track. I'm not personally familiar with it, but that is a new guidance product that's being used. And when we asked a few of the centres, RSMC La Reunion mentioned that they are providing 5-day wind radii forecasts that are using a statistical dynamical model, and so there's more information on some of these developments in the report itself. And I just want to take a moment to look at the figure on the right there, because this is a personal favourite of mine. I'm always looking for good examples of impact-based forecasts. And I really like the earliest reasonable arrival time graphic from the National Hurricane Centre as a really good example of something that is really in line with the theme of the workshop to help decision makers in their work. Because what it's depicting here is effectively the time that your storm preparation should be concluded. Well, that's my interpretation. I'm sure someone in the room will tell me if that's wrong. But the earliest arrival time of those tropical storm force winds or gales is really when it starts to become too dangerous for preparations to be made. And so rather than just provide a track, this particular product has really given some actionable information to the emergency management community. And I think it's a really nice example of providing better information for decision makers. And so I think, you know, that for me is something that I'm always looking for good examples of impact-based products. I'd love to see more, so if anyone wants to show me some more good examples that are being developed or already in use from around the world, I'd love to see it. Because I think it's these sort of products that we need to think more about, more than just the traditional cyclone track maps with cones on them. The final part of our report was looking at changes in the outer size and structure under a future climate scenario, and we started off with an example here looking backwards. So this is an example from reanalysis data. The report itself has got graphs for all of the basins, and we've just pulled out one here to highlight for the Western North Pacific. And if you look back over the last 40 years or so, there's not really been any significant changes throughout any of the basins in terms of the outer size of the system. And so you've got the 4-quadrant radii here for gales, plotted in the colours, with the black being the average. And so it's been fairly steady, and pretty much all of the basins show that same lack of an increase or decrease when you look back over the last few decades. And that primarily was from real analysis data sets, but can also be performed by looking at cool SST wakes or the output from climate model simulations. So again, I thought that was an interesting finding to look back and see that there hasn't really been a trend. And so then what happens under a future climate? This is some of Ben's work, so I'll do my best to represent it, but what he basically did was took the output of the global climate models and initialized the GFDL hurricane model on a 6-kilometre grid. And so what he's plotted here is the control run in the current climate is shown in blue. And then the future climate scenario, RCP 4.5, is shown in red. And what the graph is showing you is a radial cross-section of the winds. So this is all based on Atlantic storms. But as you can see, if you pick any one wind value, there's not a lot of change in terms of the radius of that particular wind value. For example, if it's a gale, you do see an increase in the wind speed at the radius of maximum winds, closer to the storm centre. But there isn't really a discernible or significant change in terms of the outer size of the system. And this is really in line with what most studies are tending to suggest for the outer size of the cyclones, that they're really unchanged through to the late part of the century. But that is, of course, despite the changes that are expected in terms of intensity or the wind itself closer to the core. A lot of the focus of research has been on wind. We've heard that a bit this morning as well. But there really isn't a lot of studies looking at how the outer precipitation will change. So that is an area that I think is ripe for further research under a future climate scenario to look at how the precipitation will change. And as mentioned earlier, there's really an incomplete understanding of what are the most important factors at play here. So still some more opportunities for some research to be done. And I think we'll skip over those and we'll call it there, because I think Liz will give us a summary of the recommendations. So we did have a few, that presentation's in the folder, but I think Liz, you're going to summarise the recommendations from all of our reports at the end of the session. So I'll wrap it up there. Thank you.
Thanks, Chris. Great. Our last subtopic topic is on mid-latitude interactions and structure changes, and that'll be given by Kim Wood from Mississippi State.
All right, so we are transitioning, sorry, that was a terrible pun, blame the jet lag, to talking about phase transitions. So instead of thinking about parts of the TC structure, more thinking about structural evolution. Huge thank you to our topic leads, Matt and Liz, for helping us along the way. And I must acknowledge Yanase Wataru-san for how much work he did in making this report possible, as well as our wonderful working group members. So, phase transitions, we're not just talking about extratropical transition here. So, compared to the previous IWTC, where ET was specifically reported on, this particular subtopic included other aspects of a cyclone life cycle that involved transition. So TT is for tropical transition, the process of a non-tropical cyclone becoming a tropical cyclone, and a subtropical transition where the storm is entering a subtropical phase. So in our report, which you can see online, there are these 6 sections, which we'll cover here in short order, because this is a summary. But I do want to emphasize that it's important to be thinking about, hello, Fly, the components of transition beyond extratropical transition. Hit guy really likes me. So from IWTC-9, sorry, it's kind of far down here. It might be hard to see. The recommendation was to develop a definition of ET that builds on cyclone phase space, but takes into account different pathways to exotropical transition. And so something that I want to defend is a challenge to the community to take a holistic approach to multiple transition pathways. So extending beyond exotropical transition, looking at all these different ways that cyclones can evolve and take on tropical or lose tropical characteristics. So we have various ways that we can classify tropical cyclones, some of which are used operationally and some of which are focused on with respect to research. Now, ideally, we will have an approach that classifies all types of cyclones and their transitions from one type to another. That's what we need in order to achieve this goal of a holistic approach to classifying a cyclone. Now, this cyclone phase space, or CPS, has been widely used since it was introduced about 2 decades ago. It looks at 3 components: an estimate of the thermal wind in the lower part of the troposphere between 9 and 600 millibars, an estimate of the same parameter but in the upper troposphere between 600 and 300 millibars, and an assessment of the thermal symmetry or asymmetry of the cyclone in the lower part of the troposphere, where a tropical cyclone tends to be relatively symmetric and a non-tropical cyclone tends to be relatively asymmetric. These 2 diagrams shown here classify a tropical cyclone, or TC, a subtropical cyclone, or SC, and an extratropical cyclone, or EC. These acronyms are going to come up a lot, so I wanted to make sure that I defined them. And so by traversing through cyclone phase space, we see this evolutionary life cycle of the phases of a tropical cyclone. It would be great if all cyclones were cooperative and actually followed these pathways, but of course nature is much more complicated than that. For example, when trying to define the end of extratropical transition, the point at which the cyclone is extratropical, for cyclone phase space, or CPS, that's when it attains a cold core, when thermal wind shows that it has a cold anomaly in the center. And generally, that point at which it attains a cold core agrees with the time when a TC became an extratropical cyclone in the NHC best track. Note the word generally. However, when we apply the exact same parameters, when we compute them from a high-resolution reanalysis like ERA5, which is quarter-degree resolution, it could not determine 33% of the samples for that end time of extratropical transition due to instant warm seclusion, nature not cooperating with this phase space that had been developed, partly because we were capturing nature better with that higher spatial resolution. So these are examples of going through cyclone phase space by comparing thermal symmetry along the along the y-axis and lower level thermal wind on the x-axis. And this is the nice traditional one that's behaving as we expect, and then there's the instant warm seclusion that doesn't. So here we are stuck to some extent on not being able to use cyclone phase space as we get more advanced data to work with, like higher resolution reanalysis fields, for fully capturing the life cycle of this cyclone. We also looked at the dynamics related to extratropical transition. High resolution simulations have examined diabatic processes unique to ET that increase the asymmetry and size of tropical cyclones. Really important when you're thinking about impacts and hazards. One of the themes that we've been talking about a lot so far this week. Also, the cyclone itself doesn't necessarily have to be nearby to cause impacts. The process of ET impacts downstream regions through not just that direct approach, but through diabatic initiation of Rossby waves, which are affected by mid-latitude environmental conditions. one of the takeaways from that, if a tropical cyclone undergoes transition and becomes an ex-tropical cyclone, it can be stronger than an ordinary ex-tropical cyclone, one that was never tropical at any phase in its lifetime. Recent work has highlighted that those impacting parts of Europe can be on the stronger side when looking at their maximum wind speed at 10 meters. So it's important to keep analyzing this when we think about the impacts from ex-tropical transition. All right, this is always fun. Sorry, it's a lot of text, but this is the National Hurricane Center glossary entry for subtropical cyclone. And I always love sharing this in my tropical meteorology class because my students are like, huh? They have characteristics of both tropical and ex-tropical cyclones. Okay, which ones? Well, they have organized moderate to deep convection, that makes them more tropical, but they lack a central dense overcast. That deep convection tends to be a bit more removed from the center, and they derive a significant portion of their energy from baroclinic sources. Doesn't say how much, just significant. And generally cold core in the upper troposphere, often associated with a upper level lower trough. You know, nice, straightforward definition to use to define parameters to tell us when it's subtropical. Not so much. But if we can create this intermediate category of what a subtropical cyclone is, we can develop a more accurate description of transition processes and capture more types of cyclones, such as metacanes, which often tend to exhibit these subtropical characteristics. We need a more quantitative definition regarding the fronts and the convection associated with something that would be considered a subtropical cyclone as opposed to an extratropical cyclone. An NHC team is working on a revised definition and seeks additional objective tools, so it's not like this problem is being ignored. But they need insights from the research community and from other forecasting centers that also look at these types of cyclones to consider what would be a good approach to objectively identifying when a storm should be considered subtropical. Looking at the other side, tropical transition tends to occur when cyclogenesis processes are associated with precursors that are subtropical or extratropical in nature, including upper level troughs. One thing we noticed in the recent 4 years since IWTC-9 is studies are expanding away from the Atlantic to look at this question of tropical transition and examining regions like the North Pacific and the Mediterranean Sea. Again, mentioning metacanes. Metacanes came up a lot in our working group's efforts to review recent progress since IWTC-9 on this topic. So it's important when you're thinking about making a holistic definition to consider how are storms varying in their characteristics and behavior through these transition processes depending on the basin in which they're located. Looking a little bit more operationally, thinking about, okay, there's these types of cyclones, what about when they transition from one type to another? The Bureau of Meteorology focuses on subtropical transition of TCs, such as the early stage of ET from Jones et al. 2003, but have types depending on the characteristics of the storm and the environment in which they're located. And recent work has shown that a deep warm core of a tropical cyclone became shallow after it transitioned, after it went through subtropical transition. So going back to that earlier definition of a subtropical cyclone being cold core in the upper part of the troposphere, that's been observed in the South Atlantic. So let's go back to this cradled and captured idea. So we see in these different characteristics that there are synoptic changes depending on what type. There's an approaching mid-latitude trough for captured versus a ridge in place for cradled. So here we are, they're both going through subtropical transition, but the environments are different. And so this would impact how we would try to create a holistic definition. I won't go through all of the different characteristics for the sake of time, But I think it's important to see these and realize that both of these relate to the transition process, but for different physical reasons. Operational centers apply their own classification methods based on cyclone phase space, which I outlined earlier, but also looking at these different patterns, such as what was shown on that particular table, looking at the structure of the fronts and at cloud patterns. So where is the convection and how is it organized around the center of the storm? At JTWC, they have a worksheet that uses a bunch of different criteria to assess whether a storm is considered subtropical. And SIMS is working on an automated version to apply this worksheet in a more objective manner. Some of the characteristics that they look at include asymmetry, so they compare the ratio of the long axis length of the storm to the short axis, look at how much cloudiness is present, the nature of the circulation, and the distribution and intensity of the vorticity associated with the storm. Operational challenges. No, none of these methods are perfect, but they are what they have available. But it's not just how do you classify the storm, but it's also how do you talk about the storm for those who might be in its path. During and after ET, these storms can cause disasters due to their unique dynamics. Not only can the storm itself expand, get to latitudes that often don't experience storm surge or strong winds because they've gone through ET, but also predecessor rain events can cause distant rainfall, heavy rainfall at times, from these storms. How predictable they are when they're going through transition is different than how predictable they are if they aren't transitioning. So this diagram highlights reliability for all cases, the blue line, and selected transitioning cases, the red line. The red line's worse. So what this is highlighting is that it's a bit harder to capture what the storm will do when it's transitioning versus when it already is a tropical cyclone. One problem with communication is if you change the warning type after it's transitioned, people may hear that as, oh, the storm won't be as bad, even though the impacts may not really have changed, but the nature of the storm has. So impacts-based local warnings are critical, as are collaborations with other centers to ensure consistent services, consistent messaging. Everyone's saying the same thing. It's a lot easier to trust it than when you're hearing 3 different things about the same storm. Looking ahead into the future, thinking about current patterns, we did get the first climatology of ET published since the last workshop. And that was used as a motivator to think about how would you characterize future changes in ET frequency and strength, depending on which model's being used and how you're classifying them. So something I want to highlight here is that a historical run was compared to a future run to assess how often ET occurred, and they had to use modified CPS parameters to capture these storms. So even here, CPS is not quite, it's good, but not good enough to fully capture what is being studied here. They also found that whether a storm went through tropical transition affects whether it will undergo ET, how it would undergo ET later if ET occurs. So the pathway that a cyclone follows can impact its later behavior. And as the climate warms, it's more likely that subtropical cyclones can become tropical cyclones, heightening the need to be able to characterize and track what subtropical cyclones are doing now. So to reiterate, the work that the working group did on this topic really highlighted that we need a holistic approach to these various cyclone types. Note that I gave that recommendation from IWTC-9. Not a lot of progress has been made on the characterizing TC type front. So this is motivating that we need to do this. And I'm skipping that because that's going to be covered by Liz. So thank you very much for your time.
So I'm just going to do a quick summary, just by, as I said, looking through the IWTC-9 recommendations and just putting up a few points, reiterating some of what actually Rob said this morning about the progress that we've made on generally tropical cyclone size and structure since IWTC-9, and then looking forward to what recommendations we think should be perhaps posed out of the reports for IWTC-10. So just quick outline, just basically what I said. And so there were 5 specific recommendations from IWTC-9 that seem to relate to tropical cyclone structure changes. And this first one on tropical cyclone track, I'm actually going to kick down to topic 4 tomorrow. So we'll pass on that one. The second one was number 4, and this was looking at continuing research on secondary eye wall formation and eye wall replacement cycles and the associated structure and intensity with those. And as Rob pointed out this morning, he gave it a green light, I think, a green rating. And this is just a very quick summary of a lot of the work that's gone on that was presented today in the first talk. So really done a lot on this, but still actually there's still a lot of research needed potentially if we want to actually move some of this into usefulness for operations. Still very highly theoretical. There was a second recommendation around secondary eye formation and eye wall replacement cycle, and that was finding a consistent definition of the onset, including confidence levels that would be appropriate for both research and operations so that it would be easier to transition knowledge that was produced through research into operations. And it turns out that there's been very little progress on this particular recommendation. So we're going to be passing this one through to IWTC-10 in a slightly different format with perhaps a pathway forward. Develop a definition of ET that builds on cyclone face space. This was the IWTC-9 recommendation. And you've just heard very strongly from Kim that not very much has been done on this. And so again, this has been revised based on what we now see as the need for the future, and will be passed through to a recommendation for IWTC-10 that you'll see in a minute. And then the last one from IWTC-9 was this one to routinely analyze structure parameters and post-analyze them, and then put quality controlled information into the best tracks databases for all basins so that, particularly so that it can inform research that would be useful for operations. But also estimate their errors and put that into the best track databases as well. And you already saw that out of 7 centres that responded to the survey that was sent out, there's varied amounts of this already being done in different basins. So if we move through to out of the reports and out of those presentations that have just been given, what the recommendations, consolidated list of recommendations we have for IWTC-10 to consider. The first one is that we recommend a consistent definition for SEF and ERC onset be made. This is basically the same recommendation from IWTC-9, but we're suggesting that there might be a way forward by asking the Working Group on Tropical Meteorology Research to facilitate a workshop where this can be discussed. So this might be a way to move this particular recommendation forward. The second recommendation for IWTC-10 is advancing numerical weather prediction, tropical cyclone structure prediction capabilities. So basically the idea is to be able to improve tropical cyclone parameters out of the numerical weather prediction models to the extent that we can now do better prediction of the follow-on hazards for waves and storm surge, for example. This is seen as being particularly important when we're trying to consider evolving structures with these different types of cyclones. So we're transitioning between tropical cyclones to subtropical cyclones to ET. These evolutions can happen very quickly, and seeing a need that in order to do impact-based forecasting associated with these particular cyclone types, that the numerical weather prediction is probably the way forward to be able to do hazards-based or impacts-based predictions. The third one, develop high-quality wind structure data sets. So these are data sets that will allow particularly research to be able to be done, but in an operationally relevant framework. So the context here is partly that a lot of research is being done over long term, but based on metrics for wind size that are not the same metrics that are used in operations. So how you then take that knowledge and translate it over into operations, it becomes a little bit more work to be able to try and do that. But the research community really needs to be able to use data sets over a long period of time, multi-decadal, for example, that are based on the same parameters used in operations, so that actually that knowledge transfer is a lot more easy. The fourth recommendation is to be able to develop a comparison list, okay, of the current methods that are actually used in operational centres to analyse, diagnose and predict wind structure, including during phase transitions across all operational centres, basically to be able to see what techniques exist and where gaps exist at particular operational centres, and then where the opportunities for further development of these kinds of techniques lie. So first of all, identifying where operational centres don't have techniques that exist that could fill the needs they have, and then look at where the development needs actually are. The fifth one is around the topic on outer structure and the environmental influences that affect changes in outer structure of tropical cyclones. Seems like over the last 4 years, there's been more research looking at different environmental impacts on outer structure size in tropical cyclones. It's added to the list of important environmental parameters without really being able to key in on what are the important parameters out of this expanded list. So the recommendation here is that there needs to be some more work investigating, not just are there more environmental parameters that are important for tropical cyclone outer structure and size change, but which are really the key ones, and when do they affect the tropical cyclone. And the final recommendation is for the development of a holistic approach to consistent definitions of the multiple cyclone types of extratropical cyclone, subtropical cyclone, and tropical cyclone, and the transition pathways between those types. The suggestion is that maybe it builds on cyclone phase space, but extends it as needed using additional information. And again, a way forward, because this is a carryover again from IWTC-9, is that a way forward might be for the working group on tropical meteorology research to look at facilitating a workshop between interested operational and researchers in order to try and work through this particular problem. And I think, apart from some questions for the breakout sessions, I'm not going to read through these. I don't expect you to necessarily work through all 5 of them, but these are just to help guide your discussions this afternoon. And with that, thank you. And I think I'd like to ask my co-rapporteurs, please come up and help field any questions if there are any.
Right, we have some time for questions both from online participants and from the floor. Those online, the panelists, if you raise your hand, if you want to ask a question. And if you're an attendee, you can put a question in the Q&A. So do we have any questions from the floor first? Yes, Greg. And we have one online as well, so we'll follow that.
Thank you. Firstly, I'd have to say that I've really enjoyed today. There's been some terrific stuff, and I wasn't aware of how much advances there'd been. We're talking about differences between IWTCs. When it comes to intensity and structure, I think there's been as much advance, if not more, than any other two that I know of. So it's a congratulations to everyone. I had a concern. We've got all these, we've got tropical transition, extratropical transition, subtropical cyclone, and we're sort of going on and on and on. And are we not killing the science with definitions? Let me give you a couple of examples. Just to take one that I'm very familiar with, East Coast lows were lumped in with subtropical cyclones. I can assure you that a classic Australian East Coast low has quite different structure to a subtropical cyclone in the North Atlantic as they're defined. And I can also show you cross-sections through East Coast lows where you'd look at it and you'd swear blind it was a tropical cyclone, and I could show you others where you swear blind it was in the Antarctic. So basically, it's not like there's some sort of dividing line. There's not. We're making these things up. And the second point there is, even if there is a dividing line, how do you do it? A subtropical cyclone is defined as something with a low-level warm core. Well, so what? Does that mean if it goes to 500 millibars that it's a tropical cyclone? There is a lot of variability out there, and I think we're starting to kill the whole process by trying to define too much out of it.
I loved that. I'm so glad you highlighted that there's an incredible range, in part dependent on where it is in the world. Where one of the things that's come up in a lot of the breakout sessions so far is that oftentimes we're taking assumptions about what we know from Atlantic tropical cyclones, because that's where the most recon's occurring, and we're trying to apply that to all cyclones across the world when they behave differently in other basins. So point well taken that it might be that we are trying to overprescribe things. However, I would argue that there is still merit in trying to have some definitions, because that is a forecaster need. They do need to know what types of things could be happening, and it does help to constrain it. But on the research side, I would agree that we want to avoid overprescribing and just think about instead what is the structure that we're seeing for a given cyclone.
We'll go online to Jack, if you want to unmute and speak.
Yeah, can you all hear me?
Yes, we can.
Okay.
If you can
Long
speak up
running
as loud as you
topic
can,
for me. Let's see. There we go. Okay, long running topic for me, and to answer what Greg just said, when it comes to mixing baroclinics and diabetics, nature has got more recipes for that than a bartender has cocktail recipes. So yes, that does complicate things from the definition standpoint and from the operation standpoint, as one of the reasons that we need better definitions and better analysis of what's going on. The reason we try to distinguish some of these subtropical cyclones is that they more resemble tropical cyclones in getting a lot of their energy from the diabatic energy, as opposed to the more baroclinic dominant systems. And hopefully this will work. I'm going to share my screen for just a second here, because this is not just an academic exercise. We've got a system in the Atlantic right now, the one in the middle of the picture, that at least has some chance to start down this transition path during the next 48 hours. As a matter of fact, the GFS is showing a system with a central pressure below 980 millibars, which for a baroclinic low at 28 to 30 north would be highly unusual. That in itself would suggest that we've got a potential subtropical or maybe tropical transition case at work. But over the next 48 hours, we're going to have to try to assess this situation using phase diagrams, using simulated satellite imagery, using any other information we can get our hands on, and turn this into a forecast and an analysis of what this storm is. And I'll show you just one thing here. The simulated satellite imagery off of the GFS for this particular case. And here's what the evolution of that looks like. And you can see there is some fairly intense convection associated with this system, but it's not particularly well organized around the center. Maybe by about 2 days' time, it gets a little better organized. And that picture in particular, you see a little sliver of an eye wall trying to form. And maybe there it gets a little bit more concentrated. So the question I would have, if we're going to pull the trigger on advisories for this system as compared to handling it as a marine gale or marine storm, which certainly would certainly could be a viable alternative in this case, is what it should be the criteria that we're looking for to try to do this. And that's one of the reasons we're trying to come up with a better definition of subtropical cyclone at NHC to help us with these decisions. And as Greg said, a lot of these cases will have a variety of structures. Some of them will be more baroclinically dominated. Others will be more diabatically dominated, and they will go through different evolutions on the phase space. The one thing the phase space does not show us is the diabatic contribution to the evolution, and that's one place perhaps where things need improvement. So sorry to take up so much time on this. We got a real life example of this that I could show you to highlight everything that's going on here. So
you're making Eric a bit nervous, Jack, but he does have a question coming after you, but we'll take that as a comment, I think, rather than anyone want to. No? Okay. Well, thank you for the live discussion. I don't think we need a response right now. That can be succinctly portrayed for this case.
And I guess and this ties somewhat in with what Jack said, is that, historically, the reason that subtropical cyclones were kind of started in the first place is because they were pretty close to tropical cyclones. And if you look nowadays, I don't know, 9 out of 10 eventually transition in the Atlantic basin for what that's worth. And so what are we even, I mean, we've been struggling to come up with a real definition for 15 years, longer. We've made changes to it, and you showed the definition. I was laughing the whole time because, it's how do you actually make a forecast with this analysis? It needs to be cold core, it needs to have this, it needs to have that, and the history behind that definition. There's no examples. There's no, anyway. It's a really difficult problem because what are we trying to solve? What are we? Is it a science challenge? Is it an operational challenge? When subtropicals become hurricane force with eyes, okay, yeah, we should really be focused on that. But if it stays a 40-knot system over the open ocean, is that something that busy tropical cyclone centers need to focus on? And it's a quandary.
Thanks, Eric. We have a question online. It's an anonymous question, so you'll have to introduce yourself, but go ahead.
Yeah, this is Rob. I'll just read it. It's written down from an anonymous attendee, but the question is, one of the big problems with historical agency wind radii being interpreted as, quote, structure and the ability to estimate useful metrics like IKE from them is whether the estimated wind radii is based on a mean wind or a transitory gust. For example, 1 minute, quote, sustained. Are scatterometer winds nowadays means or, quote, adjusted to be 1 minute? That's the question.
So I'm going to dodge that and see if there's someone from the satellite observation group here who can answer that.
So I think that in general, if the satellite observation is a lower spatial resolution, you can consider 10-minute sustained winds. And right now, the only one that is really high resolution is the SAR. So the SAR is typically considered a 1-minute sustained wind. I think Alexis can confirm that, but that's how we usually do.
Any other? Yes, Andrew.
Nothing groundbreaking, but since it hasn't been mentioned and following on from the same discussion, one of the biggest problems with particularly R34, when we talk about size, is operationally or in research mode. How do you separate the cyclone from the synoptic environment that it is embedded in? You can have gales extending a long way into the monsoon or into a subtropical high when they're, yeah, and so that becomes a significant problem for both subjective and objective analysis.
Yeah, I don't have an answer for that, obviously, AB. But that would be one of the great questions that could be asked at a workshop like this. One could argue, I suppose, that those research studies that are using the R5 as an outer size indicator are going well beyond those outer potentially environmental.
Perhaps I should note that we do task our forecasters with attempting to analyse. Imagine removing this cyclone from the environmental flow, taking into account the shear, so you're not expecting it to be symmetric necessarily, but have a crack at trying to write down what are the wind radii associated with this cyclone that you don't think are just purely from the synoptic field.
Sounds very subjective, but yeah, one way to do it.
And just to continue that flow of a discussion for the techniques and the development of structure in terms of NWP output, it's like, when does the model see the end of the gales? Because we see large values, and this is for validation, all that, how we go about constructing our forecast. What do we say to people? They don't care if the gale is coming from the cyclone or not. It's just a gale. So there's a kind of a succession of issues that go from NWP aspects to right through to the service delivery on gale radius, and it hasn't really maybe come through the working groups, this issue, which at the practical forecaster level is a key issue. And I just note, a forecaster idea of structure is more focused on gale radius, because that's the impact kind of into, against the modelling people who are looking in a core structure. There's a kind of quite a difference in what we are talking about.
Definitely sounds like an impacts-based bias there, forecasting.
Oh,
and a good way to do it. Well, impacts-based, yeah.
And Joe, it's even more complicated than that, because, and we could just use the example from Nicole very recently. How big do you, so hit the east coast of Florida, large high pressure system. How big do you draw those wind radii on the northeast side? And it's not academic at all, because there's even an additional layer, because you try to think about, Andrew's comment about removing the system from the synoptic, which is nice, but you also have what happens when it becomes involved in other systems up the coast. What happens when you're trying to transition from tropical warnings to non-tropical warnings? In post-analysis, what do you define as the R34? Most of the time, we define it as what we did operationally, but is that necessarily associated with the tropical cyclone, or is it just there because of the synoptic environment? Newsflash, it's just there because of the synoptic environment, but we're not going to modify. I mean, how would we modify it in post-analysis to come up with some figment of our imagination of what it would have done if we separated it? It's just as a warning center, we have to focus on the hazard. And so, in some sense, the science suffers, but we're a warning center. So I don't know how you really resolve that.
Yeah, so in Australia, we do have our figment of drawing a magic line in our post-analysis. So that we do that. So there is I hear the global consistency.
I'd love to know
argument.
how, actually. I'd love to know how.
Come to my training course. Yes.
Sounds like another cyclone dance.
Pete Black, you've got a question online. If you can unmute yourself.
Yes, I have a question for Kasuki. Hello, Kasuki. It's good to see you.
Hello.
You have the unique situation of having flown into Category 5 typhoons in the Western Pacific, which practically I don't know if anybody else, except some of your colleagues, may have had this opportunity. I just wondered, with this perspective of having actually been flying within a tropical cyclone, typhoon, Category 5, and being able to observe the distinction between the inner core circulation and the environmental circulation as you were coming and going, dropping signs along the way. What do you think, where do you think is the future in terms of being able to get a more unique and rapid assessment of this distinction between the inner core and the tropical cyclone environment that was just being discussed?
So I'm not sure I correctly understand Pete's question, but I think asking the structure of tropical cyclone in the Western North Pacific, right? No? What is your question? I'm sorry. So I'm sorry. Could you shorten your question? I'm sorry. I cannot get your question.
Sure. I cannot hear you too well with your mask on there, but I just wanted a concise question. So my question is, in terms of the future outlook, what do you think is would produce a more rapid insight into the distinction between the environment around the tropical cyclone and the inner core circulation? Similar to what has just been discussed. Sorry if
Okay. Okay, thank you very much. So I'm not sure I'm a right person to answer that question, but in the Western North Pacific, I believe many aircraft reconnaissance flights has been conducted recently, and I think that helps to understand the nature and relationship between the inner core structure and environmental situation. I'm sorry, I answered your question correctly or not. I'm not sure, but yeah, that's my answer. I'm sorry about that.
We'll go to Craig.
Yeah, no, thank you. I just kind of wanted to continue with where Eric had left the conversation and some of the other comments made about focusing on the hazard and the impact when we talk about a system that's transitioning. And I think that's a key part of it where we need to remember about the communication aspect. We try to educate the public about a tropical cyclone has these really intense hazards, particularly the winds near the center. That's why we put out a track map to help support that communication. And as it becomes less tropical, those hazards and impacts are, as we've heard, and we know they've become more removed from the center. They can be further downstream. At the same time, they can be just as severe. So having this other name for these systems, if we do it well, should support the communication of the hazard to the end user. Whether that needs to be a definition that's in science or not, maybe a scientific definition isn't the answer, but it kind of explains a big desire why there's that need to have a different way of communicating what it is that's causing the hazard that we're concerned about.
We'll take that as a comment.
Yeah, we'll take it as a comment, but I just want to say thanks, Craig, for raising that. This is something that we have to deal with a lot in New Zealand because we don't, I would need to be careful saying that. Who knows what will happen in the future. We don't normally get a landfalling still tropical cyclone, so they've always generally transitioned by the time they get to New Zealand. And so we are dealing with the case where we've had a tropical system with some pretty significant hazards that's well captured in well-established guidance and TC warning products and track maps and that sort of thing. But then they go through the transition process, and that leaves us with a question then on what do we do? What product set do we use? And part of my thoughts when the question was raised earlier on, are there too many classifications, ST, ET, TC, all the acronyms? My gut reaction was, does it matter? The public won't care. They just need a good warning product. But at an operational centre, we have procedures that define which products we can and can't use. And so in New Zealand, it is a consideration around how we communicate the hazard with a system. And so one example is that we continue to use the name. We dropped the tropical, but we continue to use, for example, Cyclone Craig, I'll use your name. So we don't call it tropical cyclone, we call it Cyclone Craig. And the reason that we do that is that the media has been focused on it while it's been up on the tropics. Comes through an extratropical transition phase, but we still need to get a really high engagement with the warning suite that's coming from the National Met Service. So communication of the hazard is really important. And that's where we do bend the rules a little bit to continue to use tropical products, even though it's not a tropical cyclone anymore. And I think that's one thing that we've got to be really conscious of as a community, that the public don't understand all this academic talk that we're having here. They just want a good warning. And so you do have to bend the rules sometimes to use the products at your disposal that have the largest reach, perhaps, is one consideration, or that the media are already congregating around as it's a cyclone coming out of the tropics. Just a perspective from home.
Rob will read a question from online.
Yeah, so this is from Eric Lai, and the question is, the term, quote, post-TC, end quote, is a bit confusing. Is subtropical cyclone included? Also, under the context of public warning, post-TC suggests a less threatening storm, but we know that is not necessarily true. Shall we brainstorm a better term? Eric is laughing behind me.
Yeah. I don't think it is the role of this body to tell centers what to label storms, but I do believe that it is worth discussing, since the goal of this workshop, the theme of this workshop, is to support decision making. And so we want our terms to support making the right decisions. So like what Chris was just talking about, where you bend the rules a little bit to keep using the products that are relevant to getting the message across so people can make decisions, that's what's important. Is post-TC the right answer? I'm not equipped to comment on that. I have an opinion, but I'm not going to comment on that because I don't see that as our role. Our role is to discuss what are the implications of the terms we're using so that we can support good decision making through the warning process.
Just seeing if WMO had an opinion. Go ahead, John.
Yeah, just like.
Sorry, Mayor, John, just a minute. We do have opinion. Okay. Cyril.
Well, it's not specifically the WMO opinion as such, right? A formal WMO opinion is something that is being discussed and but with the frequent interactions we have with user community, DRR people and stuff, I kind of support the points by Chris. The public and even disaster management are not especially interested in the technical details of what a system is, right? Whether it is called X, Y, Z, in terms of description, not the name. I'm not talking about the naming process here. But is it a warm core or whatever? They just don't understand the subtleties and all the technical or the scientific implications behind. What they are interested in is what to expect in terms of hazards, in terms of possible actions that will allow us to minimize the impacts. And those products like earliest time of arrival of really help the scenario building they have to make in such situations. But you know, when we started to work on impact-based forecasting approaches, and by the way, allow me to share that the wording of impact-based for me is a bit strange. Should be impact-focused or target, but not we don't base the forecast on impacts. We try to go beyond the forecast towards the impact. Anyway, and so when we started developing this more than 10 years ago, the key part of the key message was switch from what the weather will be to what it will do, right? And this is what interests people in general.
We have some responses to this. Andrew first and Eric.
I will, I think, come to the defense of Chris in the sense that, yes, while the public don't necessarily want to care about whether it's a subtropical cyclone or a tropical cyclone, although there is the word tropical cyclone, that can have a particular emotional response that doesn't come with subtropical, so they pay more attention. But there was another point I think that Chris was making, and that I'm sure all operational centres will appreciate, is that there are different sets of products that we put out for tropical cyclones that we don't put out for necessarily for subtropical in some places or for extratropical cyclones. And there can be some real world impacts from that. By that I mean, recently in Australia, there's been a bit of legislation passed that means that where we used to be in the rules, in terms of, maybe we'll keep calling this a tropical cyclone operationally to keep people's focus on it. I'm not going to go into the details, but because of this piece of legislation, we've kind of got our hands tied and we have to be very, unfortunately, strict to a definition, because the definition of a tropical cyclone, the Australian definition of a tropical cyclone is now in legislation. Not something that anybody here would want, and I certainly didn't want it, but that's the reality.
And so I'll just comment, and you know, the term post-tropical cyclone was kind of adopted by the Hurricane Center. It was first done by, as far as I know, the Canadian Hurricane Center, because they often get by these transition cases, and it was a way for them to continue the same products for a system that wasn't a tropical cyclone, and that's why we eventually decided to do it. I mean, Hurricane Sandy kind of sealed the deal on, you know, we had our hands tied and not able to put up hurricane warnings when we weren't expecting a hurricane, and that didn't work out very well. So we changed the operational procedure. We could have a good debate on what to really call it, post-tropical cyclone. Now we have potential tropical cyclone, and post-tropical cyclone, they have the same initials, and that really is a little confusing. Usually they're not close to one another. But I do think it was a good service enhancement to have post-tropical cyclones for the community. I mean, we're able to continue advisories for systems that are no longer tropical cyclones. We don't have to change the warning criteria, change to marine warnings, for instance. And people see the same products that they've been seeing, and they don't have to switch to. In the U.S., you'd have to switch to a whole new center to get the national product. So it's, I think it's more good than bad. But I could definitely talk to. You're not the first person that doesn't like the name, that's for sure.
And last question, John. I'm going to ask you to be very quick.
Yeah, I'd just like to follow up on that last comment and on what Chris was saying earlier about in New Zealand, what they get is almost always post-tropical cyclones. You're not even getting the transition process with all the explosion of dynamics that the post-tropical cyclone. I actually think there's a scientific reason for sort of classifying a post-tropical cyclone because subjectively, I don't know how many people, a lot of people have studied transition. I don't know how many people have studied what there is on the post-transition, but they're different. It's different to a cut-off low or an occluded low. And among other things, it seems to have a much longer life cycle as a distinct system. It tends to, carry rainfall, have a large rainfall area for much longer. So I personally think it would be worth exploring, the classification of post-tropical cyclone as a discrete system that you can continue the warnings and so on for, because as I said, it's a subjective opinion of mine, but I'm pretty sure there is a scientific difference. One of the big ones is it's got a long life cycle, whereas something out of baroclinic instability, even occlusion, even cut-off low, has a very transitory life cycle. So it's sort of a statement, I guess, rather than a question.
Okay, we'll finish there, and we're just going to go to a break, but we just want to explain the breakout process. And we're just going to clarify where we're going to, if we can. Okay, so in the same locations, you're in different breakout rooms. Your name is on the sheets out on the wall. You can take. Here are the 6 recommendations, and although Liz put up the questions, we're going to ask you to focus on the recommendations, and Kim will explain that in more detail.
All right, so I wanted to briefly go over what has been given to you to prepare for these breakout sessions. First of all, as mentioned this morning, a key outcome of each IWTC are the final ratified recommendations. Ideally, we have about 25. Notice we had over 30 from the previous IWTC, and past IWTCs have had similar numbers. We want them to be actionable, we want them to be motivating, and we want them to be reportable in 4 years. Not completed, but hey, we were able to make some sort of progress on this. So unlike past workshops, the topic leads coordinated with the rapporteurs and the working groups to create draft recommendations for this community to discuss. So every single time one of these QR codes has been displayed with this tiny URL link, that's for all of you. That's not just for the leaders and the note takers. That's for all of you. At the end of every single document linked here for each topic are the draft recommendations that we would love for you to discuss in your breakout groups. The discussion questions, they are not exam questions that you have to answer. They're there to help you think about how might you discuss the recommendations. The draft recommendations are intended to prompt discussion. Are they relevant to your experience and needs within your role in our community? Is there anything missing from the recommendations that you feel is a critical need for us to consider? The notes submitted by the note taker should be a synthesis of the discussion. Did new recommendations or revised recommendations come out of your discussion? Did recommendations get axed that you think should not be considered? The jam boards are in there to facilitate discussion. Not everyone has the same level of English speaking ability. And the Jamboards are there so that we can still get your input in written form in case you're having any trouble communicating what it is you want to say during a breakout. So please feel free to use the Jamboards as you'd like, but for the note takers, your notes are going directly to me as the chair of the recommendations committee for consideration by the recommendations committee, so that on Friday we can present a refined list of recommendations to ratify. We have an hour and a half on Friday to go through all those recommendations. I don't think anyone wants to linger hours past that to talk about the recommendations. So use these breakout sessions to think about the recommendations that have been proposed and give us feedback on how they could be changed, modified, or whether they're even relevant to, again, your experience and your role in our community. Are there any questions that I can address before we go to break regarding what your role is in the breakout sessions?
All clear.
Either that or nothing made sense.
Okay, so just the timing, we're going to have a half an hour break now, and then go to your, so at 4 o'clock, go to breakout room time. You have until 5:30. If you finish your discussion early, you can, of course, leave. I will just make an announcement on a very separate type of issue, but a local issue. We just had a 6.2 tremor about 300 kilometres southwest of here. I don't think anyone felt the ground move. This was about just over an hour ago. Did anyone feel anything? I think so. Okay. Just refreshing evacuation procedures. It is outside and down out of the car park. Not that I'm trying to scare anyone. And Fakri would like to make an announcement, but we are starting at 8:30 tomorrow in here. We're having a demonstration with live data on the cyclogenesis 7-day forecasting in the Australian region before we go to topic 4. I'll pass over to Fakri.
Yeah, thank you, Joe. Yeah, colleague, just a few minutes ago, 2:17, we have an earthquake here, 6.2, but we cannot feel it because it's far away from here, 300 kilometers south of Bali. So we just want to remind you again the safety briefing. So Murni, please.
Thank you, Mr. Fahri. I would like to remind you about safety briefing. In case there is earthquake or fire, you can move to the parking area. Later, the staff hotel will guide you to the evacuation site. So in case there is earthquake and fire, you will move to the parking area in front of the hotel or in front of Denpasar, Bali. In case you in your room, you go in front of the hotel, parking area in front of the hotel. And then I will also remind you that excursion already closed, but if you still want to join and still not yet fill the form, you can tell me. I will help you. And then Mr. Paul Gregory. Where is Mr. Paul Gregory? Yes, this is your key card. Thank you, only that. Thank you very much. One more time, I forgot to remind you, tomorrow for excursion, just wear your casual clothes, yes, because we're gonna go to Uluwatu. There's a very beautiful beach in Bali. We'll enjoy performance, we'll enjoy sunset over there. So just wear your, comfortable clothes that you think okay with you, okay? Thank you very much.